So I welcome all the participants to day 3 of our online faculty development program on optimization technique, theory, practice, and emerging application. Today we have two sessions. In the first session, we'll discuss about the teaching learning based optimization, which is called as a TLBO, and also we'll discuss about one of the extension of TLBO algorithm that is called as Joya algorithm. And in the second session, we will discuss about differential evolution algorithm and its case study. So if you have installed MATLAB, I request all of you to open the MATLAB. Once we'll discuss the theoretical part of TLBO, we'll see how to implement the TLBO algorithm. And I will discuss about the Jaya algorithm, the theoretical part. As a task, you can implement the Jaya algorithm. Once you understood that how TLBO works, you can easily implement Jaya algorithm because it is very simple in comparison to TLBO algorithm, right? So first we will focus on the first TLBO algorithm. It is also a very popular algorithm, like we discussed about genetic algorithm. We will discuss tomorrow or day after tomorrow about particle swarm optimization. We have already discussed about end colony optimization. So if you go to the literature, you will find these algorithms are very popular algorithms. Means most of the people have applied these algorithms. And if you see citation of these papers are very high in comparison to other optimization algorithms. Then once you are comfortable in TLBO, Joya is an extension of TLBO by combining both phases of TLBO. So this algorithm is quite simple in comparison to TLBO algorithm. Okay, so TLBO or Joya algorithm, both algorithms were proposed in the literature by Professor Dr. Ravi Pudi Venkat Rao. He is professor in higher academic grade pay in mechanical engineering department of NIT Surat. So also we have another session tomorrow related to Rao algorithm, and these three variants of the Rao algorithm also proposed by Professor Rao. So in 2011 he proposed this algorithm. You can see the citation of this paper. I will give the reference to this particular paper. I'll also share this paper with you. This paper is having one of the highly cited paper in the field of soft computing or optimization technique. So this TLBO, teaching learning based optimization, it is a population based method. Like you have seen, we have taken set of population in the case of genetic algorithm, and we apply the process or different, you can say, operators on these population in order to generate children, right? And we compare the performance of the children with the parent. If a parent is better, then you need not overwrite the parent. But if children is better, then you can overwrite a parent. So again, the objective of the TLBO and genetic algorithm, they all algorithms are same. Our objective is to reach to close to the global solution, right? So this particular algorithm uses population of solutions to proceed to the global solution, right? Like many mathematical problems are there for which we know that which one is the global solution. Okay, so if you want to try to solve that particular problem using any soft computing technique or any optimization technique, then you will see in those techniques after iterating is for 20 iteration, 30 iteration, 50 iteration, whatever value you will get, that value is close to that solution, optimal solution, right? And teaching learning based optimization is based upon our classroom teaching. But genetic algorithm, if you compare with the TLBO, genetic algorithm is based upon the chromosome, especially male chromosome and female chromosome, right? So there are two parts you can see in this algorithm. One is called as teaching phase, another is called as learning phase. right? First one is called as teaching page. Second one is called as learning page. So what actually basically we are doing in the first page, teaching page, a teacher talks about a particular topic and the number of learners in a particular class, right? So if you consider the knowledge level of these students, let's say you consider knowledge level as for a particular student in terms of a particular value in between 0 to 1, right? For example, I consider this user is having 0.2, this user is having 0.3, this is 0.7, and so on. So after a teacher talks about a particular topic, if a particular student understands that particular topic, his knowledge level is increasing, right? You can say he understood means some more knowledge is added to uh, the existing knowledge, right? If a student has not understood the concept or he is not attentive in the class, then you can say the knowledge level is same. So basically in the teacher phase, the main objective is to learn from the teacher. Once you learn from the teacher, then you can see whether your knowledge level is improving or it is same. But in genetic algorithm, what you can do when you take male chromosome and female chromosome, and suppose we generated two different child, then if their parents are good, not necessarily the children are good, right? So there may be different behavior. Maybe they are better than their parent. Maybe they are worse than their parent also, right? So once teaching phase is over, once classroom teaching is over, so these students will interact with among themselves, right? For example, like if I number it by 1, 2 and 3, 4, 5 and 6, 7, 8, 9. So each student has to pair with another student. Like once class is over, let's say student number 1, roll number 1 is interacting with class roll number 8, right? And it is also based upon their choice. So they will discuss whatever covered in the whatever topic covered in the class, and this interaction also will give a better knowledge to both of them, right? So sometimes this interaction is not also fruitful, right? So after interacting 1 with 8, you have to again check the knowledge level of 1 and knowledge level of 8. If knowledge level is increasing, then you have to accept it, otherwise you have to reject it. So the second phase is related to this one, that is called as learning phase. So when they reach to their hostel, they make a pair. Okay. Suppose one is make a pair with 8, and 2 can also make a pair with 8. Okay. 3 can make a pair with 7. 4 can make a pair with 7 also. Right. There may be a duplication also. Not it is a distinct or unique one, right? So we learn by interaction between the learners. So these people are learners, right? So learners are communicating each other or interacting each other to understand the topic in more better way or clear and the things which is not covered in the class, right? So in this way, actually, this teaching learning based optimization works. So let us take a mathematical function, right? You can take anything as a case study. So as a case study, I am taking here a mathematical function, which is a very famous function. We call that as a Himalblau function. Okay. And the objective of this Himalblau function is it is a minimization problem. It is not a maximization problem, right? Like I mentioned you genetic algorithm case. Genetic algorithm are usually used for maximization problem. So if a minimization problem is given to you, you have to convert it into a maximization problem. So here we are given with the Himalblau function, which is f of x is equal to x1 square plus x2 minus 11 whole square plus x1 plus x2 square minus 7 whole square, right? So this f of x, okay, or f function f is represented in the form of two variables. One is x1 and another is x2. So once you know the value of x1 and x2, if you put in this particular formula, then you will get the value of f of x. But how to know which x1 and x2 value is better, right? or in which x1, which value, which pair of value of x1 and x2 will give you this function is the minimized one, right? So you may take x1 value anything, x2 value anything, but you will see with a pair of x1 and x2 value, the value is minimum, but we do not know what is that particular value. So our objective is to find the values of x1 and x2 such that we can minimize this particular function, right? Now, while we are talking about x2, x1 and x2, this is also present in a particular state space, right? So here, the x1 and x2 value is within the range of -5 to +5, right? You can see x1 values are -5 to +5. x2 value is also in between -5 to +5. So their range is already given. So whatever value you want to take, you take, but you have to ensure that the value is in this particular range. It should not go outside this range. Like some optimization algorithms were while we are solving that problem, x1, x2 value exceed this particular range, right? For example, if I say x1 is equal to x1 plus 1, right? Suppose your x1 value is 5. So 5 plus 1 means x1 value will go as 6. But you can see, if you look into the limit of x1, then the maximum limit is 5. So it should not exceed 5. So in that case, we fix that particular value in the as a boundary value, right? Even if it is 6, we fix it as a 5 because we cannot exceed that particular boundary. Or you can reject that particular solution as well, right? So this is the problem. Is the problem is clear to you? Is it clear? We have taken a function, then our objective is to minimize that function, and the range of x1 and x2 is given to you. You have to choose a value of x1 and x2 for which f of x is minimum, right? Okay, somebody has written something in the chat box. Yes, somebody, Nilesh sir is asking about online MATLAB. Yes, anything is okay. There is no issue. Online, offline, both are same, right? Only you have to write the code. Whatever I'm writing here, the same code you have to write. Otherwise, I'll share the code. If you don't have MATLAB, at the point of time, you can execute that MATLAB code, right? So let us solve this problem using TLBO. Later point of time, I'll solve the same problem using Jaya algorithm, right? So let us consider a total number of students in a particular class is 5, because it is a numerical calculation. I cannot take a very large value, right? So simply I have taken total number of students in a class is only 5. This total number of students is also called as our class size. It is also called as the population size. So the population size is represented by a variable m, which is equal to 5. Assume that you are teaching in a particular class, and number of students in your class is 5. So let us, I represent these 5 different students. I can say serial number of these 5 students are 1, 2, 3, 4, and 5, right? Now, each and every student studies some subject, like in our semester pattern, we have 5 or 6 subjects, right? So assume that the number of subjects is equal to 2. You can take as many number of students, as many number of subjects, but for a numerical calculation, I have taken a very small values. Otherwise, calculation is very difficult, right? I'll show you the code with any number of student, any number of subjects, right? Okay, so here I have considered 2 different subjects. Let us call 2 subjects as x1 and x2. So here I told you this function f is represented in the form of x1 and x2, right? So, but you have to ensure that the value of this x1 and the value of x2 should satisfy this particular range, that is in between -5 to 5. So these subjects are also called as your decision variables. Okay, they are called as your decision variables. And In genetic algorithm also we have studied, right? There is a termination condition. I told you termination condition sometimes we take after 20 iteration or 30 or 50 iteration, will stop at that particular period of time. So let us consider that we want to iterate this only one time, right? After one time, whatever result is we are getting, that result we have to accept it, because if you do more iteration, then again a lot of calculation is going to come, and this is only theoretically valid. Don't take the number of iteration as one while you are going for the implementation. It will not give you the good result, right? You have to take 20 iteration, 30 iteration, then only you can observe that whether your result is good or bad. Now what I have to do? So it looks like a 5 cross 2 matrix, because 5 number of students are there and they are reading two different subjects, or they are enrolled in two different subjects. So it looks like a 5 cross 2 matrix, right? So initially I have to guess what are the values, right? What is their marks or some value, some numeric value for a particular student in a particular subject. So we generate this subject in the range of -5 to +5, right? So you can follow any distribution which we have studied in the MATLAB. Generally, when you go for any distribution, you can follow that is there in the mathematics. But if you go for MATLAB, then you will see it is generating the random number by following uniform distribution, right? So if you have opened MATLAB, I'll show you how to generate the random number. Okay, you can simply write RAND, and if you put a parenthesis, open parenthesis and close parenthesis, and if you press enter, then you will get a value in the range of 0 to 1. Okay, so what I'll do, I'll share also this thing in the chat box. Okay, so if you want some values in the range of 0 to 1, you simply write RAND. But if I need a value in the range of 0 to 5, but it is not an integer, so you can specify RAND multiplied by suppose 5. So if I need a particular value within the range of 0 to 5, okay, so it is coming as 4.5. So it will generate a random number and multiply that random number by 5, right? So we are getting here 4.5290. But sometimes in some optimization problem, we want to actually generate the random number, but that should be an integer without this decimal point. Okay, so in that case, you can use a function that is called as random I. I stands for your integer. Then you have to specify how many values you want to generate. For example, in this case, what is the dimension? In this case, what is the dimension? 5 cross 2. Suppose I want to generate a matrix of size 5 cross 2, right? Matrix of size 5 cross 2, suppose in a particular range. Okay, so suppose I want to specify -5 to +5. Within this particular range, you generate a matrix size of 5 cross 2, right? Okay, there is a comma missing here. You can put comma also in between -5 to 5. So you can see now we have generated the values in between -5 to 5 for both x1 and x2, and these values are nothing but your integer values. There is no decimal point values. So if I multiply this value with this RAND, right, which gives the values in the range of 0 to 1, definitely these values will come in the range of -5 to 5, but these values are your decimal values, right? So you have to use this random integer function by specifying your lower limit, or you can say I minimum, integer minimum. This is called as I max, integer maximum or upper limit, and size of your matrix. Like here, I have taken the size of matrix is 5 plus 2. As much as big matrix you can do it, right? So by default, it is stored in a variable that is called as ANS. But if you want to store in some variable, for example, I want to do this one, but I want to store this variable in A, right? I have taken a temporary variable A. So you can see in the workspace, now I have created a variable A, and if you go open this A, then you will see all the values are in the range of -5 to +5. Is it clear up to this? Okay, let me save this one, this code also. We'll do the whole code. Okay. Now what we'll do here, as I told you here, randomly we have to generate the initial population, right? So for initial population, what you require, you need how many students are there in your class and how many subjects they are studying. Okay, if you know this information, you can generate this 5 × 2 matrix. For example, so this is the random matrix we have generated, right? When you generate in MATLAB, you may get a different matrix. Just I am showing you a snapshot, right? Where I got all the values are in the range of -5 to 5, and they are the decimal values. They are the decimal values we have generated in the range of -5 to 5. But whenever you do different run, you may get different values. That is the problem, right? So you can take a snapshot of this value while doing the coding, so that you will see whatever result you will get to our hands-on calculation, the same result you are getting through MATLAB. Okay, so let us go to write a code, simple code. So all of you create a new script. If you have installed your MATLAB, all of you create a new script by click here and save it in somewhere, right? Save H. Let's say I want to save it in. Okay, I want to save it in my desktop with the name TLBO. Okay. Now, what we did, how to generate this random number? You know the number of subjects and number of students is required. So you can write simply a for loop, right? For I is equal to 1 to students. Okay, for j is equal to 1 to subjects. So if I write, suppose I want to generate this population, we call this a population, right? So I can write population is a two-dimensional matrix. So I'm representing it by I comma j, and each and every value you can generate by specifying, but you have to specify the lower limit followed by the higher limit, and as you are showing one by one index, so you can write it is 1 comma 1. But if you want to generate 5 × 2 matrix, you have to specify 5 comma 2. In that case, loop is not required. So this will give you an integer value, right or not? We have seen this particular one is going to give you an integer value. But if I multiply it with a RAND, then it is going to give the values in the range of -5 to 5 only, but these are decimal values. So this is the simple code. If here I have not specified what is the student size, what is the subject size. So you can take, suppose I'll write here the static declarations. At the point of time you can change based upon your need. Suppose I want writing student is 5, number of student is 5, and number of subject is 2, right? Similarly, specify what is your lower limit. Lower limit is given in this problem, it is -5. Similarly, higher limit is given as +5, right? So if you do this one, then automatically it is going to give in the range of this value, right? So you have to click this green button, that is run. It is written run. If you execute it, you will get the values in the range of -5 to 5 and all the decimal values. So go to your yes, now it is executed. Where we have stored? We have stored in the population, right? You can search for population here. If you open it, then you can see all these values are in the range of -5 to 5, but they are decimal values. Is it clear up to this? Any question? Okay, there is a question in the chat box. Okay, let me see. Can we put LB and H bound in? Yes, yes, there is no issue. You want to specify here, na? There is no issue. You can do it. Only I am writing here because later point of time, if you change this one only, then it will go. It will run. So my usual practice is that whatever standard, whatever constant values you are taking, better to write here the static values. So later point of time, suppose we have decided that this time we'll take limit minus 15 to plus 15. So there is no need to come to code, right? You can directly change here. So it will affect here, right? That's why we are doing this one. Instead of random integer, right? Please increase the font size. How to increase the font size? Just a minute. View. Okay, just a minute. Let me see how to increase the font. Okay, this is bold. It will not work. Okay, let me click Control plus plus. Is it working? Control plus plus. Control. Can anybody help me to increase the font? What is the command? Can anybody say? Control plus plus should work. Just a minute.
Sir, control plus.
Control plus is not working, madam. I have already tried. Control or Control C plus plus, it should work. Just a minute.
So control plus scroll, plus mouse scroll.
Control, acha. Control plus, okay.
Mouse scroll. Is that
Increasing, no. There is a font here. Somewhere it is there. Okay. Okay, I'll paste this code in the chat box. I'll copy from there. No, it is working. Usually Control plus plus should work. Okay, leave it if it is not working. Okay, so we have generated a metric size of 5 cross. You can see here, we have generated a metric size of 5 cross 2, right? And if you open your workspace, and there if you click a population, you will get this matrix of size 5 cross 2, right? So what we are going to do in TLBO after generating this 5 cross 2 matrix, if I ask you to calculate the function f of x or f of x1 and x2, so what you will do? You have to simply put the x1 and x2 value in this particular equation, right? for example, if I put x1 value here, right? Like x1 value I am taking as 3.22. X2 value is 0.403, right? Okay, 0.403. Then if I put in this equation, so it is nothing but 3.22 square plus 0.403 minus 11 whole square plus 3.22 plus 0.403 square, then minus 7 whole square. So can anybody calculate this one using your calculator? Smartphone calculator also you can use. Calculate 3.22 square plus 0.403 minus 11 whole square plus 3.22 plus 0.403 square minus 7 whole square. Can anybody calculate and tell me? So calculate and check that are you getting 13.139 or not? You may get slightly a different value if you have not taken all decimal places. Can anybody calculate and tell me? Any answer? Somebody suggested home tab preference font. Okay, let me go to MATLAB. Okay, we'll see later otherwise. Okay, so you will get here 13.139. Similarly, if you put x1 value as 0.191 and 2.289, you will get the value as 77.711. Like that, you can put x1, x2 values, and you can get the values of the value of f of x1 and x2. Right now, what I will do, I have calculated for all the 5 different population. So the objective of this particular function is to minimize. So out of these 5, you know, the best solution is the solution number 1. Okay, where we got the value is 13.139, and other f of x values are more than that. Okay, so out of these 5, obviously the first one is better. So after finding this f of x value, if you go to the algorithm of TLBO, first you have to find what is the mean of x1 and mean of x2. So you have to calculate mean of x1, that is nothing but 3.22 plus 0.191 plus 3.182 plus 1.66 plus 2.214 divided by 5. So you'll get the value as 2.093. Similarly, if you calculate mean of the x2 values, you will get the value as 1.697. Okay, so once you done with this one, now you have to calculate that this x1, x2, x3 or up to xn, these are the different subject. 1, 2, 3, these are nothing but the students' serial number, right? So now we have to calculate difference in mean for each and every subject. So what is that difference of mean? We will see. We have calculated the mean, right? We'll see what is the difference between how much distance of each and every student's x1 and x2 value from the mean x1 and x2 values. So in order to calculate difference in the mean subject, you have to use this particular formula. That is dj is equal to uj xj star minus tf into mj. So don't go through these mathematical formulas. It looks very complex. Try to understand what is there in this in this particular formula. So here u is nothing but a random number in between 0 to 1. Okay, that is uniform distributed random number. So we assume that these two numbers are 0.25 and 0.43 respectively. Now you have xj value, xj star. Xj star is nothing but you can see that the best population I told you out of this 5 population, after calculating the f of x value, you got the value as 3.22. That is the best value for x1, and 0.403 is the best value for x2. Because with these values you are getting the f of x value is the minimized one. Right. Now what you will do here, there is another factor that is called as a teaching factor. So teaching factor is calculated using this formula, that is round of 1 plus u, or simply you can take teaching factor is equal to 1. Because suppose if I choose a random number here, it is saying round of 1 plus u, right? So if I write round of 1 plus a random number, let's say the random number is 0.1270. So we'll get round of 1.1270. So it is 1 only, right? So in some cases, we simply take it the teaching factor is equal to 1. Now this mj is nothing but mean of each and every subject, which we have calculated in the previous slide. Mean of the subject is 2.093 and 1.697 respectively. So here you are taking the best population and mean values of all the population. Using these values, what you can do, you can calculate difference in mean for subject 1 and subject 2. So let us see how to calculate. If I take subject 1, so let's say for subject 1, my random number is 0.25. So I'm writing 0.25. Then xj value is 3.22, right? 3.22 minus teaching factor is 1 and mean value is 2.093. So if you calculate this, you will get the value is 0.2818. Right? Similarly, if you calculate for second subject D2, you will take this random number 0.43 multiplied by 0.403, which is nothing but the best value for x2, minus 1 into the mean value, that is 1.697. So you will see, if you calculate it, you will get the value is minus 0.5564. Okay, now you got these values using the best population and mean of all population. So now the next step says that in TLBO, you have to add this D1 value and D2 value to all the elements of X2, X1 and X2. So we actually find from the best population to the mean population, what is the distance or the difference, right? That we are going to add to each and every population. So here you can see this is your population. This part is your population, which is there in the previous slide. Then I am adding D1 value. D1 is equal to 0.2818. Okay, and D2 is equal to minus 0.5564. So these two values we have added into each and every population. First value is for x1, second value is for x2. So now what you got? You get an update value, update x1 value, update x2 value. Earlier, this is your x1 value. This is your x2 value. Once you add or here a subtract, you will get an updated value of x1 and x2. But what is the guarantee that updated value is giving you good result? You need to find. So after updating the first one, let's say for population 1, I'm solving for population 1, or you can say student 1. Okay. So x1 value is nothing but 3.5018. x2 value is nothing but minus 0.1534. So if I put x1, x2 value in this particular equation, that is nothing but x1 square plus x2 minus 11 whole square plus x1 plus x2 square minus 7 whole square. So if I put in this equation, I will get the value of f of x. So if you calculate this one, you will get f of x is equal to 13.3037. Now, if you go back to the first population before updated this solution. What is the value? 13.139. So now you tell me new value is better or old value is better? Old value is 13.139. Okay. Sorry, new value is 13.3037. Old value is 13.139. Which value is better out of these two value? Can anybody answer?
First one, sir.
First one is 13 point old value is better because this is a minimization problem, right? So you have to find out of these two value which value is the minimum value. Here you can see after decimal point 1 is there, right? After decimal point 3 is there. So old solution is better, right? Similarly, we have updated the population for 2, right? If you update the population, you are getting f of x value is 92. But if you go back to the previous slide, here you can see what value we are getting, 77.711. So if you compare it here, which value is better? Again, old value is better. It is minimization problem. If it is a maximization problem, yes, new value is better. But if you go for population number 3, 4, 5 after updation and after calculation of f of x, so we found that this one is better, right? Right, because 14 is the old solution, new is 12. So obviously it is better. Here you can see new solution is improved a lot because it is 261, it is 136. And here it is 43, it is 39. So last 3 cases, new solution is better, but first 2 cases, old solution is better. So if new solution is better, you keep it and replace with old solution. Right? If old solution is new solution is not better, simply discard it. Okay, you have to simply discard it. Right, in this way actually you can solve the very first step of our TLBO algorithm, right? But this is not the complete one, right? So see what we are going to do here. Now the teaching phase is over. We have updated, you have calculated the difference in the mean subject 1, difference in the mean subject 2. Then you have added or subtracted whatever value it is coming based on that, and you got updated value. Now this updated value, after updating the value, you have calculated f of x, and you have compared with your old f of x. If new f of x is better, you are keeping it. If new f of x is not better, you are discarding it. Right? Is it clear up to this one, first phase? Any doubt in the first phase?
So for first 2 serial numbers, you are taking the old values, and for the rest 3, you are taking the new values.
Exactly, madam.
Is it?
Because their f of x value is better.
Okay, thank you.
Right. So now, if you go for the second phase, I told you second phase is a learning phase. In learning phase, interaction will happen between 2 different learners. So how many learners we have taken? We have taken 5 different students. So there are 5 learners. So each and every student has to pair with another one, right? So one should pair with one learner, 2 should pair with something, 3 should pair with something, 4 should pair with something, 5th also need to find a particular pair. For example, if you see here, let's say 1 is pairing with, okay, 1 is paired with 2, 2 is paired with 5, 3 is paired with 1, 4 is paired with 5, and 5 is paired with 4. Okay, so after this pairing, you can notice that here 2 is paired with 5 and 4 also paired with 5, and there is no one paired with 3. You can see this one and say that 3 is paired with 1, but I am telling by looking into this particular column, nobody has taken 3 as to pair with that particular value, right? That particular learner, right? Now what you will do, if you do interactions, definitely either there is a improvement or there is a, you can say there is no, the interaction is not successful. Means where where you are before the interaction, you will be in the same place, right? So let us see how the interaction happens between 1 and 2. So here you can see I have taken the population 1. So this is your population 1 or student 1 and student 2, their respective x1 value and x2 value. And this is their corresponding f of x value. So in order to say that this interaction is successful, what you will do, you have to generate two different random number again. Let it be 0.47 and 0.33 respectively. And you can calculate after interaction again, the knowledge level is going to be updated. So in order to update the knowledge level of both x1 and x2 of the learner number 1, so you have to use this particular formula, right? What is this particular formula? If I want to update this particular value, I have to take old value plus this random number, use a, that is nothing but I have taken here it is 0.47 and best minus worst. How will know which one is best, which one is worst? Best is obviously whose f of x value is better. So in this case, best is your 1, worst is nothing but your 2. So best means I am going to take 3.22 minus worst means 0.1910, right? If you calculate it, you will get the value as 4.6436, right? This is for variable x1, the subject x1. Similarly for x2, what you will do? You will take the old value. Let's say the old value is 0.4030 plus second random number, that is 0.33. Then what you will do? You will take best minus worst. Best minus worst means 0.4030 minus 2.2890. So that will give you the value as minus 0.2194. So after this interaction, you got the value, the updated x1 and x2 value is this 2. But again, the same question, what is the guarantee whether this, you can say this two values are giving you good result? There is no guarantee. So in order to check this one, I am calculating f of x1 value as 4.6436, x2 value I am taking minus 0.2194. So if I put in this particular equation, I am getting the value as, let's say, 112.3816. So before interaction, my f of x value is 13.1390. After interaction, my value is 112.3816. So tell me whether interaction is successful or not. Interaction is successful or not? The updated value is 112.3816. Yes, exactly. Interaction is not successful because you are getting a higher f of x value and it is a minimization problem. So what we will do? We will discard these two x1, x2 value. We'll say, okay, before interaction, whatever value is there, we are going to keep that particular value. Right? So retain the old solution, discard the new solution. Right? Now, this is the interaction between 1 and 2. What I have to do? I have to do the next interaction. Next interaction is between 2 and 5. If you remember, go back to the previous slide. 1 to 2 interaction is done. Now we'll go for 2 to 5, then 3 to 1, then 4 to 5, then 5 to 4. 5 different steps you have to do. Okay. I'll show you one more. So if you do with the 2 and 5, these are the values of 2 and 5. And their corresponding f of x value. How to update their value? Update their value means I will take 0.1910, this particular value, okay, plus a random number that is 0.47, okay. Then these two difference, that is 0.1910 minus 2.4958, right? Then similarly, if you go for the second variable, you will take 2.2890 plus second random number is 0.33. Then difference between these two, that is 2.2890 minus 0.3106. So you got a new x1 value, new x2 value. Put this x1, x2 value in this equation. If you put, you are getting the value as 53.3166. But what is your earlier solution? It is 77.7110. But now your solution is 53.3166. Tell me which solution is better, whether old one is better or new one is better. Yes, new one is better. Subankar sir answered. Majumdar sir has also answered. Okay, new is better. So what I'll do, I'll eliminate this old solution. I'll say update the population to with minus 0.8923, 2.9419 and 53.3166. In this way, you have to update. Is it clear? Now you have to make another interaction, that is with the 3 with someone, right? I told you 2 with 5 and 3 with 1, 4 with 5 and 5 with 4. After interaction, you will get these values. What is I have given here, all the values, right? So now you can see what is the best solution before when we start this test first page. What is the best solution? The best solution, if you remember, the first solution is the best solution. And it has not changed in the teaching phase, as well as it has not changed in the learning phase. So 13.1390 is our best solution. Now, after the first phase, means after one teaching phase and one learning phase, you can see now the best solution is 12.3875. So solution is improved from 13.1390 to 12.3875. Okay. Similarly, if you do a couple of iterations, you will see it will again reduce to some other values. Is it clear up to this? Any doubt up to this one? Any question? Okay, if it is clear to you, let us go for the implementation part. Okay, so what we did here, we have already generated the population. After generating population, what we will do? We have to calculate the mean value, right? And a series of steps you have to repeat. This calculation of mean, calculation of fitness, and calculation of difference in mean of each and every subject. This process you have to repeat it couple of times. That's why I'm taking for I is equal to, or you can take k as the loop because I will use for other purpose. K is equal to 1 to number of iterations. And for this particular example, I have considered number of iterations as 1. Okay, just I'll show you that the same value we are getting in the coding also. Okay, and once it is done, then you can run for any number of times. Right? Now, how to calculate mean? In order to calculate mean, you can simply write for I is equal to 1 to students, right? And for j is equal to 1 to subjects. I'll show both the slide and this one so that you can visualize clearly. Let's see this one. Okay, I'll write here so that you can map easily. Okay, this is the population which we have generated. Now we are calculating the mean. So I'm writing for I is equal to 1 to student, for j is equal to 1 to subject. We are calculating mean of each and every subject. So j is equal to, how will calculate mean of j plus population of ij, because in population I comma j, sorry, there is a bracket mistake here. Mean of j plus population ij contains your values. This will sum all the values. First, we need to sum all the values that is present in x1 column. Then, if I divide by 5, okay, because number of students is 5, then I will get the mean. So, mean of j and population of ij. Okay, after end of this loop, I will again run a particular loop. Okay, j is equal to 1 to students. Mean of j is equal to mean of j divided by students. Okay, so these two will help you. First one is actually not calculating the mean, it is summing all the values like 3.22 plus 0.191 plus 3.182 plus 1.660 plus 2.214. And this particular loop actually divide by 5. Okay, so you will get value is 2.093. Okay, let us close this one, because every for you have to end, right? Every loop you have to end. But as you run this code, you will get a different mean value. Now it is showing some error. Okay, it is showing mean j is equal to mean j. Yes, it is an error because first you have to take mean value, because in the right part also I have taken mean, right? So that's why it is showing error. So better what we can do, I'll simply declare mean is equal to, I will initialize with all zeros of 1 and subject, because it is a 1 cross 2 matrix. Right now I think you will not get any error. You are getting one error. Index exceed the matrix dimension. Okay, mean zeros 1 subjects. Okay, subject divided by student. Okay, this is student. For I is equal to 1 to student. For I is equal to 1 to subject, meaning population of j. Okay, so it is exceeding. Just a minute, let me check. Index exceed the matrix dimension in line number 21. Go to line 21. That is mean j is equal to 1 to students. Oh, sorry, this is not student. We have to go for subjects, because there is 2 subject, right? So you will get 2 mean. If there are 2 subject, you will get 2 mean. So once you execute it, now if you open the mean value is stored in here. In workspace, you can click mean. So you are getting the value as minus 5.5816 and minus 6.9016. One more time, if you run, then you may get a different value. Now you are getting minus 4.9794 and minus 1.2891. Right? So you are not getting the exact value. Why you are not getting? Because your population, which we have mentioned here, that is different than the population considered in the current one. That is, both are different. This population and our population taken in the example, that is different. So in order to get this same one, so what you can do, let me comment this one. At the point of time, you can uncomment. I'm writing population of ij. Okay, there is no need of ij also. In fact, we can write it outside this loop also. I can write population is equal to, what are the values we have taken? 3.220, 0.403. Okay, then this column indicates it is end of one row, right? 0.191, 2.289, right? That is second one. Then I can write 3.182. Next one is 0.335, 1.660, 4.593, and 2.214 and 0.867. Okay. So now you can see I have written whatever population given in our example. So if I run this code, now the results would be same. You can check. You are getting the value is 2.093 and second value we are getting 1.697. I'm sharing this code again in the chat box if you want to copy. Somebody asked you a very good question, that is there any rule, right, to follow for pairing? There is no rule. That depends upon your random number, right? Suppose I'll generate a random number in 1 and 5, then whatever value it is coming, I'll say you pair with that one. Right? There is no rule. Okay, the first part is code is done. Now we have calculated mean. We need to calculate this one also. This we have not done. That is calculating the fitness value. So see how we'll write the code for this one. So in order to calculate the fitness, simply you have to write this long equation for I is equal to 1 to students. Okay, for each student you will get a fitness. So fitness of I is equal to, I will calculate fitness. Let us see how to calculate fitness. You have to use this equation, right? X1 square plus X2 minus 11 whole square. So what you can do, you can write population of I comma j or I comma 1. If you take, it will come the first index. First index is nothing but your X1. I is nothing but your student number. First index represents 1. The second one, that is here we are writing 1 means it is representing first index. If you are writing 2, then it represents the second index. So X1 square means what you have to do? Population of I comma 1 multiplied with population of I comma 1. Right? Now what you will do? This part is done. Then you have to take population of I comma 2. Okay, in order to calculate X2, right? Minus 11, right? So this first part is done, but it says square. So you can multiply with the same thing in order to get the square. So if I do multiplication with the same thing, and that will give you the square part. Then let us proceed for the second one. What is second one? Second one is your X1 plus X2 whole square minus 7. Right? So in that case, you can write population of I comma 1, okay, plus population of I comma 2 multiplied by population of I comma 2. You have to be very careful for the bracket, otherwise you will get error. Okay, multiply it, then minus 7. Okay, this will give you X1 plus X2 square minus 7. But I need square. What I'll do, I'll copy this one. Okay, then multiplied by this one. This will give you what? Your population. Okay, let us check we are getting the same population or not. Go to your workspace. Check for what is this? Fitness. Check for fitness. Check this one. First one we are getting 13.1392. Second one we are getting 77.7105. You may get slightly different value. 14. Okay. Next one is 261 point something. The next one is 43 point something. Okay. This part is clear. Now what we have to simulate? We have to go for difference in the mean subject of 1, subject 1 and subject 2. Right? So for that, initially you have to do, now you will calculate, reevaluate again the new population. Okay, you have already done with population. So once you add this subject value, you will get the new population. Right? So you have to take another array to keep the new population, because already you have stored the population part. You have to store the new population also, right? For that you have to take a new population array. But before that, you need to find out of these 5, which one is the best, which one is giving you best fitness. Like here I told you, the best fitness is given by the first student. That also you need to identify. How to identify that? So you will write for I is equal to 1 to students. I need to find who is the best students. So if let's say fitness I is less than, okay, fitness of I is less than best fitness, right? So you have to mention here what is best fitness, right? Let me take a very large value as best fitness. Best fitness is equal to, I'm putting number of 9s, which you will never get, right? Okay, so I'm checking with best fitness. I'm saying best fitness is equal to fitness of I. Okay, if it is less, and you have to also find which one is best fitness index, so that you can say student 1 is better, or student 2, or student 3 is better, right? That you can identify. Right now, fitness calculation is done. You will get your best fitness one. Okay, check. Let us see whether it is getting error or not. We have to check. No, we are not getting error. If you go for best fitness, it is showing 13.1392 is the best fitness. And if you look into best fitness index, it is 1. Okay, now what is our job? This part is done. Now we have to find difference in the mean subject, right? So for I is equal to 1 to subjects, here so parallelly, so that you can see and understand it clearly. Now I am calculating difference in the mean subject using this particular formula. So this formula you have to write in the MATLAB. Okay. So for each subject you have to calculate. Suppose I am calculating difference of J. Okay, let us take it to J because we are taking subject as J. Difference of J is equal to, you means what? It is a random number. I'm writing, it is a random number. Okay, or you can simply write a rand function, right? If you want to take any random number, then population, okay, best fitness index, that is your best one, best fitness index, comma J, and you have to take also teaching factor. So let it be TF, I'll declare it, multiplied by mean of J. Mean of J we have already calculated. Okay, this will give you what? Difference in each and every subject. So TF we have not declared. So TF is equal to 1 round of 1 plus U. So I am taking TF is equal to 1. Okay. But if you want to take this specific random number, which you have taken as 0.25, 0.43, then you have to explicitly mention here. You can mention random number, otherwise you will not get the same result. 0.25 and this 0.43. Okay, if you want to get the same result, otherwise it is not required. Similarly, you can see another set of random number we have used in the next page. What are the values? The values is here 0.43 and 0.33. So I'm taking that is a random number 1. So I'm writing random number 1 is equal to 0.47 and 0.33 in order to get the same result, otherwise it is not required. Okay, now this part is done, difference in the subject. Then after finding the difference of the subject, what we are doing in TLBO? We have added that value. After finding the difference of values, we go to this slide. These two are the difference in the values. What we did? We add this D1 and D2 value to all the elements of x1 and x2. So what we will do here? Write another loop for I is equal to 1 to students, for j is equal to 1 to subjects. Okay, I am taking another population. Okay, in order to compare old population with the new population. Basically, we are going to check the fitness only, right? New fitness and old fitness, and we have to decide which fitness is better. So I'm taking another new population array to save the new results. So I will keep population I comma j. Okay. Okay, it is containing your old population, right? Plus whatever value I got here in the previous loop, that is difference of j, that I have to add. Okay. This will give you a new population. Then what you have to do? You have to repeat the same process. You have to again calculate fitness for all the values that is there in the new population. So I am calling that as a new fitness. New fitness is equal to new population I1, I of 1, I comma 1, new population I comma 1, new population I comma 2 minus 11. So instead of population, I am taking new population, so that I can compare old population with the new population. Okay, now new population part is done. Right, what we have to check, whether new population is better or old population is better. So I'm writing again another loop for I is equal to 1 to students. If the new fitness value of I is greater than, okay, the fitness value of I, because it is a minimization problem. If new fitness is better, then you have to do nothing, because we have to keep old fitness as it is. But if it is not better, okay, means old fitness is more than the new fitness. In that case, new fitness you have to replace with old fitness. So fitness of I is equal to new fitness. Right? Not only that, index also you have to update. So index means there is a value for x1, there is a value for x2, that also you need to update. So I'm writing another loop for j is equal to 1 to subjects, population of I comma j is equal to new population of I comma j. Right? So this will complete your first page. So let us run, see is there any error or not. Okay, we have added and we got this one, these values. We calculate this fitness also. Now we compare this fitness with our old fitness. Okay, and those values are lower because it is a minimization problem. We say that is better. So it is expected that these values we are going to get in the output. So go to your old population and check. Open the workspace, go to population. Check, are you getting the same value or not? 3.22 and 0.4, 0.19 and 2.28. Okay, some values are changed here. Okay, why it is changed? Because of the random number. Okay, so there is a code we have written with RAND, right? That we have to change. Where we have written, yes, this code. So instead of writing this code, what you can write, you have to actually comment it and write the code such that it will take this random number, because our random number is different from the value generated by your rand function. right? So you can write here our random number is there in random number 1 comma j. Then population is same, best fitness index is same, j is same, PAP is in. Okay. Now we'll check whether we are getting the same thing or not. So this one, yeah, now you can check 3.22, 0.4030, 0.1910, 2.2890, 3.4638 you are getting. Here we are getting 37. Minus 2214 you are getting, 2216 we are getting here, 1.9418 and 17, 4.0366, 0364, 2.4958 and 0.3106. Some minor difference you will get based upon the number of digits you have considered for your calculation. Is it clear up to this? Any question? Anyone? Anyone is doing? Are you getting this result or not? Please let me know. Okay, I'll save the code. I'll save part of the code because it is not supporting the entire code in the chat box. Population gone. Okay. Let me take 4, then up to this one. It is also not going up to new fitness. It is okay. Let me copy from here. Okay, this is the code. Okay, whole code is not going. I'll share with Google Drive link later, or I'll post in the group. Okay, any doubt up to this one? Anybody having any question? So this completes our first page, right? Then we'll go for the second page. Okay, what we are going to do in the second page? We have to make pair, right? In order to do pair, somebody also asked in the chat box that somebody asked a question, is there any rule to follow the pairing? There is no rule, I told you, right? So you can generate it randomly. Suppose I'm writing for I is equal to 1 to students, and for j is equal to 1 to subjects, I want to find the pair. I'm writing pair of the first student is equal to, I'll randomly generate one value, okay, in between 1 to students. The 5 students are there. You have to pick 1 comma 1, right? One value you have to extract using this random integer function, right? So pairing is done, but in our case, what we have taken pair? We have considered the pair is nothing but first one 2, second one is 5, third one is 1, then 5, then 4. Means first student is paired with the second student paired with fifth, third student paired with 1, fourth student paired with fifth, and the fifth student are paired with 4. Right? Now what we'll do? For I is equal to 1 to students, for j is equal to 1 to subjects. Okay, I'm again going to calculate the fitness, right? But before that, you see this one. What we did here, we use this particular formula, right? The personal best, right? Their personal value, that is 3.22 plus this random number, right? Here for the subject 2, we are taking this random number. Then the difference between these two. That we have to calculate. So how to do this one? So I can calculate. Again, I am storing in the new population of I comma j is equal to, I have to take the old population I comma j plus, I have taken random number 1. Random number 1 contains these two. I have already taken. If you want to take random number, any random number, you can write array function. Okay, random number 1 comma j multiplied with the difference in the population. So I can write population difference means I can write I comma j minus population. Here I'll take, in place of I, I'll take pair, right? Pair of 1 comma I, okay, comma j, right? Okay, this will give you the result after doing this step, right? So we are expected to get these two values. Then again you have to find the fitness. So what I will do in order to find the fitness, I will copy directly this code already you have written. Where we have calculated this one. So I'm copying this code, new fitness. Okay, but here we are doing for one student, right? So you need not write another for loop here. So as we are doing with only one student, okay, we have calculated the new fitness. Then again we have to check whether new fitness is better or old fitness is better. The same loop you can take from here, but the entire thing is not required because we are dealing with only one student and its interaction with another student, right? So I'm taking, if new fitness is greater than fitness, you have to do nothing, right? Then if new fitness is less than fitness, then fitness is equal to new fitness, or j is equal to 1 to subject, population of ij is equal to new population. We end this for here and this if here, right? Another end is to, okay, that end I have already written. I am removing this, right? Now what we need, you need another one, another variable here. So this completes one iteration. You run it and see whether the same result we are getting or not. What is our object result after first iteration? This is the result, right? The result is improved from 13.1390 to 12.3875. So let us see what is our updated result. We'll go to the fitness. So these are the fitness you are getting. Check with this, compare with this one. First one you are getting 13.1390. Yes, here also 13.1392. So there is slight difference you will get. Then next one is 77.7105. It is 71.7105. It is 12 point, then 136. Okay, just a minute. Somewhere I have done mistake. How many iterations we have taken? We have taken only one iteration. Okay, that's fine. What about pairing? Okay, this pairing code need not be required. I am commenting it. Comment you can do by writing a percentage symbol. I have paired here. Then I have updated the new population as random number 1j, population ij minus population of pair of 1i j. Fitness of I is same formula, so no need to check here. If new fitness is greater than fitness 1, fitness I is equal to new fitness. J is equal to 1 to subject, 1 J is equal to, okay. Okay. Any other thing? Any random function we have used here? I have already used random. Yeah, please.
In the last loop,
Yeah.
without the for and anything, it is you are mentioning I fitness I without a for loop.
This one, right? You are saying this one.
No, sir. 71 number line.
71 line. Okay. 71 line, it is not required. Now we are checking here if, right? Here we are running for the I is equal to 1. Okay.
And that is in outside of the for loop, sir.
Oh, we are outside of the for loop. Sorry. Here, correct. You're right. That is the mistake we have done here. So what actually we can do here? This end will remove. Okay. Then new fitness will come here. Alignment is very important. Otherwise, understanding is difficult. Is it okay now?
Yes, sir.
Yeah. Okay, let us run and see. We are getting the same thing or not. There is a slight mistake here. Thank you for identifying it. Yeah, now you got, let me run again. Yes, exit. It is done to execute successfully. Go to the fitness. Are you getting the exact fitness? Yes. But the fourth case you are not getting, right? 13.1390, 53 point something, 12 point something, and 30 point something. What about population number 4? Why it is not coming population number 4? Is it paired with 5? Can anybody see? Is it paired with 5 or not? Because pairing is important. If pairing mistake is there, then definitely we will get a different value. Yeah, it is paired with 5. So it is 136. What we are getting here? We are getting the value is 136. Means it is taking old value. It is not updating with new value. But his new value is better. A new value is better. I think there is a small mistake here, right? So you will get actually if it is the value is the interaction is successful. Okay, it is giving good result. Otherwise, you will take the old value only. I think there is a mistake in this calculation in the slide, not in the code. Okay, so in this way you can run this algorithm. If you want multiple iterations, simply you have to take in iteration variable here. Let I am taking this one, iterations is equal to 1, and at the end of the loop you can declare iterations is equal to iterations plus 1, right? So it will run for the next iteration. Iterations is equal to iterations plus 1, right? Suppose I am taking the number of iteration is 2. So run it. If it is successful, then again you go to your workspace and check the fitness value. So you can see now the fitness is improved to 9.8834. After end of the first iteration, you got result here is, you can see here, the result is improved from 13.1390 to 12.3875. Now after the end of the second iteration, you are getting 9 point something. Like that, if you continue with a set of iteration, you will see, you will get the value which is close to your global solution. Okay, is it okay? Any other question? I'll check with the population number 4. I think there is a mistake in the slide. Okay, So if you've understood, again, you can see the algorithm, the same thing we have written here. First, we need to define the population size M, which is nothing but the number of students. We have to decide the termination criteria. Here we have considered the termination criteria is only one iteration, but actually in real calculation, we are taking more. Then N is the number of decision variables, or nothing but our subjects. And iteration counter starts from 1. What we did first in the TLBO, we computed the mean value, right, for all the subjects. Then after calculating the mean, we found that compute the difference in the mean, right? And also we have calculated the fitness value to identify which one is the best one, right? And once you are ready with the difference in the mean, you add that mean value to the respective variable, design variable or subject, and compute the new f of x value. Okay. After finding the new f of x value, compare with your old fx value. If new solution is better, you have to accept it. Otherwise, you have to retain the old solution, or new solution is rejected. So this completes your first page, that is called as your teacher page. And once teacher page is over, then you can go for the learner page. In learner page, what happened? Each student K choose one randomly from the rest. Okay, if there are 5 different students are there, they can choose rest 4 students for their pair, right? And allow them to interact and identify the better and worst solution in each and every pair. So you can use this particular formula to again update your x1 and x2 value, which is new xj is equal to your old xj plus a random number, best minus worst, right? So after that, you will find a new value of x1, new x1 and new x2. You have old x1 and x2. After interaction, you are getting new x1 and new x2. Find the fitness value using new x1 and new x2. Okay. So if you see that with new x1 and x2 value, your this function is better, then accept it. Otherwise, you have to retain your old f value, old function value, means old x1 and x2 value. And once you reach to the termination condition, that is nothing but the number of iteration, then you have to stop. Otherwise, you have to continue by taking t is equal to t plus 1. Okay, in this way, actually TLBO works. Any question till now?
Sir,
Yeah, please, sir.
can we actually implement TLBO for optimizing the parameters of deep learning architecture or network?
Deep learning factor, you have to train your model to get x1 and x2 value, right?
Yes, sir.
Then how will apply TLBO? Once you get x1, x2 value, suppose you can take a set of x1, x2 values. Yes, sir.
Yes, sir.
Yeah, if you get a pair of x1 and x2 value by training your model, and suppose you want to test that, suppose 5 values you have collected, and out of 5 values you want to know that which value is better. Okay, in that case you can use TLBO.
Yes, sir.
But if there are in that case you can apply TLBO. Okay, or if you want to again further optimize, then also you can use TLBO.
Okay, sir.
Okay, so rather than making a random guess, like here we have taken a 5x2 matrix randomly. So for that, generating that 5x2, getting that 5x2 matrix, you can apply other techniques instead of taking it randomly.
Understand, sir.
Yeah. Any other question, anyone? Okay. So we'll proceed to the second algorithm. You can easily implement the second algorithm because in the first algorithm, as I told you, there is 2 steps. Okay, TLBO, you have 2 different phases. But if you go for Jaya algorithm, both phases are merged to one page, right? And the word Jaya, it is a Sanskrit word. The meaning of Jaya is victory. And here the algorithm tries to find two different things. First thing, it says that in your state space, if the solution is here, okay, then you should be very close to this particular, your solution should be close to this particular point. Like if this is success, get closer to the success. That is nothing but reaching the best solution. And if you know, if there is a solution here, which is the worst solution, then in order to avoid the failure, you have to ignore this particular solution, or you have to stay away from this particular solution. So you want to do two things. One is get closer to the success, avoid failure. Okay, with these two principles, the algorithm was proposed. And like TLBO, it is also a algorithm specific parameterless algorithm. So here we took a objective function f of x. Like previous case, we have taken Himalblau function, and our objective is to either minimize and maximize. But previous case, our objective is to minimize. Here also we'll go for a minimization only. And at any iteration, you have to take m number of design variables. Design variables are nothing but your student. N is nothing but your candidate solution. That is nothing but your population size. And in order to get updated value for x1 and x2, you have to use this particular formula. Okay. So in order to get a new value of x, you have to take old value. These R1, R2 are the random numbers. XB is the best value and X is your current value. That means you have to see what is the distance or difference between the best value and your value. At the same time, that will give you success, which we say get closer to the success. On the other hand, you will take the worst value and compare with your value to stay away from the failure. Right? In this way, actually, this algorithm works. And all the accepted function values at the end of the iterations are maintained. And these values becomes the output, the input to the next iteration. Whatever value you are getting in the after end of the first iteration, that you are going to give input to the next iteration. Okay, see actually how it works. So I am taking the same problem, minimize the Himalblau function. F of x is given to you. Here also we have taken number of students as 5 and number of subjects as 2. So I am generating a 5 cross 2 matrix. Right? So this is a 5 cross matrix. Let us assume that you know how to calculate f of x. Once you know these two values, if you put in this equation and calculate 3.15 square minus 4.02 minus 11 whole square plus 3.15 plus minus 4.02 whole square minus 7 whole square, then you will get the value as 177.53. Now, after finding the fitness value for each and every population, you can find which one is best. Like it is a minimization problem, so obviously the lowest value is best. So this particular population is giving you the best fitness value. So population 2 is best. And its corresponding x1 value is this one, x2 value is this one. Now, coming to this one, this is your worst value, that is the highest value, right? So fourth population is the worst population. So your objective is go closer to 2. Your objective is to avoid the solution number 4 in order to get the success, right? Now, how to get update value? So in order to update value, you will use this particular equation. So you can see I am taking current population, which is 1, 2, 3, 4, 5 over a period of time. But which one is the best one? Best one for all the population is population number 2. Worst one is the population number 4. So you have to make 5 different calculations. You take current population as 1, best is 2, worst is 4. You take current population as 2, best is 2, worst is 4. Current population is 3, best is 2, worst is 4. Current population is 4, best is 2, worst is 4. Current population is 5, best is 2, worst is 4. This calculation you have to do. So I am taking 1 to 4. In the next case, I will take 2 to 4. then 3 to 4, 4 to 4, and last 5 to 4. Now here, this is the formula to update your or getting the new x1 and x2 value. Okay, so how to get? I'll take old value. Old value is 3.15 plus one random number. Let the random number is 0.68. Then I'll find best minus current. So best means best is 4.06 minus current solution is 3.15. So modulus of 3.15. Right? First part is over. Coming to the second part, I am taking another random number R2, which is 0.76. Okay, these are the two values for x1, but these are the two values for x2. I am taking first value here 0.68, 0.76 here. Now what do I have to find? Worst one. Worst one is 4.13 minus current one is 3.15. Okay. Worst is your 4.13 and 3.1. First you have to check these two, then you have to check these two. So you got x1 value is 3.02. That is your new x1 value. Similarly, you take 1 with 2. This for subject x2 you have to do, right? Minus 4.02, one random number, then difference between these two, which we are taking here, minus 2.22 minus of modulus of minus 4.02. Then second random number is 0.39. So 4.58 and minus 4.02. So you got this value. How to know this solution is better? You have to again calculate f of 3.02 and minus 8.86. So here you are getting a very big value, but your current solution is 177.53. But this solution is very high in comparison to 177.53. So as this solution, old solution is better, I am retaining the old solution and discarding the new solution. Right? Now go for 2 to 4. What you will do? 4.06, okay, plus 0.68, 4.06 minus 4.06. Because in this case 2 to 4. Current is 2, best is also 2. So this part you will get 0. Worst case is 4.03 and 4.06 and random value is 0.76. Similarly, for x2 if you calculate, first part is 0, second part is second random number and difference between 4.58 and minus 2.22 modulus. So you got new x1 and x2 value. If you calculate f function f x1 x2, f of x1 x2 by using these two value, you are getting the value is 1468 and your current solution is 14.60. So obviously it is very, very high. So what you have to do? You have to retain your old solution only. You have to discard this new solution. Like that, if you carry out these particular steps, then you will get these are your new values, these are the new values, and these are your old values. So you can see new value is not better, so I am taking old value. Here also new value is not better, I am taking old value. But in this case, you will get your new value is better. Fourth case also new value is better. Fifth case also new value is better. So if you see here, which one is the best solution? The minimum one, that is 14.60. After one iteration, you can see the value reduced to 1.31. So see, if you compare with the previous one, if you remember, we got 13 point something, right? 13 point something we got in the first one. And we got, after one iteration, we got a 12. Right? After one iteration, again, two phases are there. Here with a simple one, we reached to 1.31. Okay, like that, if you continue with a set of iterations, okay, you will see after a couple of iteration, your value is close to your global solution. Okay, is there any question? Anyone having any question? So you have to carry out these steps for multiple iterations, right? Again, you take these particular values. Okay, which one is the best solution? Now, best solution, previous case, your best population is 2, worst population is 4. But in this case, if you see, your best population is 3, worst population is 1. So you have to do 1, 3, 1. Okay, you have to do 2, 3, 1, 3, 3, 1, 4, 3, 1, and 5, 3, 1. So that you will get again this particular set. Then you compare with the old one. Which one is better? You see based upon that. Okay, which one is better? You see whether old solution is better or new solution is better, and choose the solution accordingly. Right. So if you are interested more about this one, I request you to refer this particular paper. That is a review of application of TLBO algorithm and a tutorial for beginners to solve the unconstrained and constrained optimization problem. It's published in the year of 2016. And an extension of this particular paper is published in Springer. So the name of the paper is Jaya, an advanced optimization algorithm and its engineering application. Okay. So these two papers you can refer for TLBO and Jaya. Yeah, thank you everyone. If you have any question, you can ask. Any question, anyone? Yeah, okay. Thank you everyone. So we'll start the next session at 5 or 5 p.m. Okay. Thank you.
Yeah, good afternoon, all. Am I audible?
Yes, madam.
Okay. Good afternoon to all. So in this session, I am going to discuss about this differential evaluation algorithm, and we'll see how to solve some problems by using this differential evaluation algorithm. So this is the outline. So we'll see how this basic differential algorithm, how it works. What are the operators used in the differential evaluation algorithm to change the population from one iteration to another iteration. Then we'll solve one example. Then we'll see, right, the code in the MATLAB. So, the genetic algorithm, it has been discussed, right? In the genetic algorithm, we are having initial population. Then, from the population, you are applying, right, selection operator, crossover operator, and the mutation operator to go to the next iteration. Right? I mean, a new set of population you are generating. So, similar to genetic algorithm, your differential evolution algorithm, this is an evolutionary algorithm. It works for the continuous function, right, where the objective function is continuous, and this is proposed by your Kenneth Price and Reynolds Strawn in 1994. Right, this is a stochastic population-based technique where you are starting from a set of solutions. That's a population-based, and stochastic means your randomness is there by using the random numbers. We are taking some decision. So like genetic algorithm, here each solution is called a genome, or this is a chromosome. The chromosome consists of number of genes, right? So the number of genes represents the number of decision variables. How many decision variables are there in the problem? Depending upon that, the length of the chromosome or the size of the chromosome has to be decided. So this differential evolution algorithm, it differs from the genetic algorithm by the operators, right? So first, we have to apply the mutation operator followed by the recombination operator, right? So here, if somebody has unmuted, please mute yourself. Please mute yourself. Somebody has unmuted. Okay. Right. So first we have to apply the mutation operator, then we have to apply the recombination operator. So here recombination operator, this is the crossover operator, like your genetic algorithm. But the process of mutation is different and the process of crossover is different than the genetic algorithm. So here the population, whenever we are creating the initial population, whatever solutions we are including in that population, that is called your target vector, right? Then we are applying the mutation operator to the target vector to get another set of solutions, that is called your donor vector. Then, after getting the donor vector, we have to apply the recombination operator or the crossover operator to get the trial vector, right? So the size of the target vector, donor vector, and the trial vector are same, and this is size equals to your whatever your population size is, suppose 5, and number of decision variables are also 5. So this is a 5 cross 5 matrix, right? So this is the initial population that we call the target vector. Size is 5 cross 5. After applying the mutation again, we are getting another population, that is 5 cross 5 donor vector. Then here again applying the recombination of the crossover operator, we are getting again another population of size 5 cross 5. Population is 5, but that matrix size is 5 cross 5. Right? Then what you have to do, right? So how to do this mutation, how to do this recombination, and what is the meaning of this donor vector, what is the meaning of this trial vector, and let us see. So those are used for entering into the next iteration. So whatever population you are generating initially, how to get the population for the next iteration. Right? Like ZA, we have followed some procedures, selection followed by crossover followed by mutation. Here we are doing the mutation followed by crossover or the recombination operator, followed by we have to do the selection, and the selection we have to do by using the greedy process. Right? As in the genetic algorithm, always we are selecting the better solutions for crossover, right? Here what we are doing, we are selecting between the target vector and the donor vector to represent the trial vector. So whether the for the next iteration, the solution will come from the original population or the solution will come from the donor vector after applying the mutation. So selection of the better solution we are performing after the generation of all the trial vectors. I mean after applying the crossover or the recombination. Right? So how to select that one? So for that simply we have to do greedy selection. So whichever solution is good, that solution we have to keep from the next iteration. So either that may come from the target vector or it may come from the trial vector. Right? So the mutation operator in the differential evolution algorithm, this is very simple operator, right? So what we are doing here, we are having the initial population, we are calling that is the target vector. This is the target, right? Suppose 5 chromosomes are there, C1, C2 up to C5. Okay. So what we are doing, we are applying the mutation on this target vector to get the donor vector. Again, donor vector, your C1 dash, C2 dash up to C5 dash you are getting, right? So how we are getting this donor vector? We have to apply this mutation operator. So what is the mutation operator here? So the donor vector of a chromosome, XI means your CI, you can call this. This is defined as B equals to, so B represents the donor vector, X represents the target vector. Here this is representing the X, this is the V. V is the donor vector. So how to define the C1 dash or the V donor vector for the first chromosome? This equals to XR1. So this is the simple formula we have to use for getting or doing the mutation operator. XR1 plus F into XR2 minus XR3. So F is the scaling factor, and that value generally in the range 0 and 2. And this XR1, XR2 and XR3, these are the 3 random solutions from this target vector. I mean the initial solution. Right? So what are the constraints you have to follow here? So R1, R2, R3, it belongs to the population size 1 to NP, and R1, R2, R3 and the chromosome for which we are defining the donor vector all are different from each other. Right? So R1, R2, R3, it belongs to the population 1 to NP, and R1 not equals to R2, not equals to R3, not equals to XI. So all the 4 should be different. So if you see here, suppose for the C1, this is the C1 solution is there in the target, right? We want to find out the C1 dash. So we have to generate 3 random numbers from the 2, 3, 4, 5, because for the C1 we want to generate, right? So out of 2, 3, 4, 5, we have to select 3 solutions, right? This is the R1, R2, R3. Suppose R1 is 2, R2 is 4, R3 is 5, right? So this second solution, fourth solution and the fifth solution will take part in this expression to find out C1 dash, right? So here we have seen that R1, R2, R3, both all the 3 are different from each other, and they are different from the first solution, that is the C1. So if you see that target vector, right, whatever the solution C1, this is not involved in the mutation, because we are applying the mutation operator like this, XR1 plus F into XR2 minus XR3. So nowhere the target vector XI, right, this is involved in the mutation. We have to choose other solutions. So how many solutions, what is the minimum number of solutions required for applying this mutation operator whenever you are solving a problem? The population size, it should be greater than equals to 4. Then only you can choose 4 different solutions, right? Because R1, R2, R3 and the chromosome for which you want to do the mutation, right? But all 4 should be different. That's why the population size, it should be greater than equals to 4 whenever you are dealing with this differential evaluation algorithm. And there are different variations of this differential evaluation algorithm, we'll see later. So in that case, the minimum number of solutions of the target vectors required, it will vary. It depends upon which type of mutation we are going to apply in the differential evaluation algorithm. Then we'll see, after applying the mutation, we are getting the donor vector. Then we have to apply the recombination, right? So there are 2 types of recombination or the crossover you can do. One is your binomial crossover, another is your exponential crossover. Right? So let us first discuss this binomial crossover, how this binomial crossover you can apply to the donor vector to get the trial vector, right? So generally the crossover, as in the genetic algorithm also we have seen, crossover you are applying to increase the diversity of the population so that your search space, you will be able to explore more search space. That is the meaning of the diversity of the population. So how to find out this trial vector now? Now we are having the target vector X is there. We have applied the mutation. We got the donor vector V here, right? Now our target is to find out this trial vector U, right? By applying the crossover operation on this donor vector, right? So what is this? Simply this binomial crossover is the creation of trial vector. It can be so the UJ, right? So UJ, this will be either it will take the value from this donor vector V or it will take the value from the target vector X, right? So either Xi will come to the solution or Vi will come to the solution. So this is the J index is J you have used. So Uj equals to, this is Vj. So the donor, from the donor vector, the solution will come to the trial vector if, right? So this is the equation for this one. If you have to generate a random number R, and this is the PC is your probability of crossover, like your crossover rate you have used in the genetic algorithm, right? Similarly, your PC, you have to take a very higher value in between 0 to 1. Then you generate a random number. If that random number is less than equals to your probability of crossover, or so there is another constraint here, J equals to 5. So what is this 5? 5 you have to select a random number, right, in between 1 to D. So if your D number of decision variables are there in the problem, you have to randomly generate the value of J, right? Sorry, you have to generate the value of 5 from the 1 to D. So why it is used, we'll see in the next slide. I will tell what is the meaning of this OR and the AND operator, right? So if R less than equals to PC or J equals to 5, the trial vector, it will take value from the donor vector. Else, for the next condition, when it will take the value from the target vector, if your R is greater than PC, random number, whatever you are generating, it is greater than your probability of crossover and J not equals to 5. 5 is same. 5 you are selecting from one of the variable out of the D decision variables, right? So what it happens here, why we are using this J with comparison to 5, right? So there must be a solution in the donor vector that will come to the trial vector, right? Because whenever we are doing the mutation, we are getting some new solutions, right? So always there is a chance that, there is not a chance, always one of the solution from the donor vector, it will go to the trial vector. That means that in that way, you can increase the diversity of the population, right? So if you come to this one, same thing, your Uj is the jth variable of the trial vector, okay? So J value will vary from 1 to D. Vj is the jth variable of the donor vector. Xj is the jth variable of the target vector. Phi is the randomly selected variable location out of D-dimensional decision variable. And R is the random number between 0 and 1. That's why I see, sir, here your randomness is there in here with the value of phi. Randomness is there with the value of R. That's why this differential evolution algorithm, this is a stochastic based algorithm, right? So because depending upon this random values selecting, whatever you are selecting randomly, right, your decision will change. How to generate the next solution, this will change. So D, right, whatever you discussed, these the total number of decision variables. So this phi, why you have used this phi, it ensures that at least one variable is obtained from the donor's vector. That means one solution from the donor vector, it will come to the trial vector. Right? So the mutation, whatever you are doing the mutation, it will allow for the diversity. Right? Then the probability of crossover, that is the PC, we generally have to keep very high in the range 0 to 1, right? So the higher probability of crossover or the higher PC, it results more variable from the donor vector, right? So there is a chance that if the PC value will take higher value, we can take more value from the donor vector. That means whatever mutation we are applying, right, we are getting those values from the donor vector. So in this way, it will lead to the increase the diversity of the population for the next iteration. Let us do one example. You will see how this trial vector is coming depending upon your D, phi and PC values. So assume there is a 5-dimensional problem. We are having 5 dimensions, x1, x2, x3, x4, x5. These are the 5 decision variables. Suppose you have selected the phi value randomly equals to 4 from 1, 2, 3, 4, 5, because these are the 5 decision variables. So randomly we have selected 4. So phi equals to 4. And this PC probability of crossover, this is 0.8. Suppose this is the assumption. So what we have to do, assume we have applied the mutation operator on the target vector, right? So we got the donor vector values are there with us. Now we have to find out the trial vector. So whether the trial vector U, right, U1 will take the value from V1 or it will take the value from X1. Similarly, U2, whether it will take the value from V2 or it will take the value from X2. Similarly, U5, whether it will take the value from V5 or it will take the value from X5. That is our target, because these are unknown values. Trial vector is unknown. This is known. Target vector is known. We have applied mutation. These values are also known. These values are unknown. So what you have to do, if you see this equation, we are having this 5 value we have selected, right? So what else we want? We want this, what you call this random number we have to generate, right? This R value we have to generate, because PC is given, phi is given, and J you can take from 1 to 5 because number of decision variables are 5. So what do you want? We want R, right? So what we have to do in this, we have to generate 5 random numbers for the 5 decision variables of the trial vector. Here you have to generate R1, R2, R3, R4, R5. So depending upon these random numbers and by using those binomial crossover equation, now we can decide whether this U1, it will come from the V1 or X1. Similarly, U5, whether it will come from V5 or it will come from X5. Now let us see, suppose we have generated 5 random numbers for the 5 trial vectors or the 5 decision variables, right? Suppose 0.5, 0.9, 0.8, 0.91, 0.25. Right? So our values U1, U2, U3, U4, U4, these are non-known. Right? Whether it will take value from the target vector or it will take value from the donor vector. Right? So that is our objective. So how to do that one? Now let us see. Suppose the target vector value, right? This is the 12, 43, 52, 87, 96, 32. These are given. We have applied the mutation and suppose we got the donor vector values at 23, 15 up to 51. Right? So our target is to find out what is this target vector values. U1, U2, U3, U4, U5, U6. Okay, 6 dimension is 6 here it is given. Okay, 5 suppose we have selected 4. Now suppose these are the random numbers we have generated for each decision variable. Now we'll see, this is 0.5. Random number is R is less than PC. Or if you remember, or J equals to 5, right? So what is J value here? J value is 1 because for the first U1 we are calculating. So 1 equal or condition, either this one or this one. So this random number is less than PC. So from where it will come? So the trial vector will take the value from the donor vector. That's why this is 23. Now next one you see this is 0.91 you are generating. So 0.91 is greater than 0.8 and J not equals to 5 also there in the AND condition, right? So as this is 0.91 greater than 0.8 and j means your 2 not equals to 4 because 5 is 4, right? So if this condition is satisfying, then it will take the value from the target vector. That's why this is 43. This is 43, right? Next you see 0.79. This is less than again 0.8. Okay, this condition is satisfying. So it will take the value from donor vector 49. Next scenario, this is 0.90. You see, 0.90 is greater than 0.8 and your j value is 4 here, right? So 4 equals to 4. So the AND condition is not satisfying. So from where it will take the value? It will take from the donor vector, right? If you see that one. If this condition is satisfying, it will take the value from target vector. Otherwise, it will take the value from donor vector. That's why this one, so this one 0.90 is greater than 0.8, but its j value is 4. 4 equals to 4, the 5 value. That's why instead of taking value from the target vector, it has to take the value from the donor vector. That's why this is 71. For the next one, this is 0.25. Okay, so 0.25 is less than PC. This is the OR condition. So this one is satisfying, means it will take the value from the donor vector. Next 0.85. So 0.85 is greater than 0.8 and here j equals to, you see, j equals to 6. So 6 not equals to 4. The AND condition is also satisfying. So it will take the value from the target vector. Now this is the value 32 will come to the trial vector, right? So we have started with a population with these values 12, 43, 52, 87, 96, 57. So if you represent horizontally this solution, suppose we are having 6 dimensional variable or 6 decision variables are there. So the solution is suppose x1, x2, x3, x4, x5, x6, right? So we have initially we have generated the value, suppose 12, 43, 52, 87, 96, 32. Here if you see, here this is written vertically, right? So this is the solution, right? From the one population, one solution is like this, or one chromosome. So what we have done, we have applied the mutation operator on this to get the donor vector. So the donor vector is now 23, 15, 49, 71, 67, 51. This is the donor vector. Now what we have applied? We have applied the binomial crossover and we got the trial vector as 23, 43, 49, 71, 67, 32. These are the values we are getting, right? So the initial solution is this. These are the 6 variables values. And after applying the mutation followed by the recombination of the crossover, we are getting these values, right? So next what we have to do, we have seen in that. So after getting the trial vector for the target vector, right? So what we have to do, we have to do the selection operator. So the selection we have to do by using the greedy selection. So now we have to see whether this solution is better or this solution is better. I mean the target solution or the target vector is better or the trial vector is better. So how to determine whether the trial vector is better or the target vector is better? Because whatever optimization problem we are going to solve, they are having some objective function, right? So we have to find out the objective value with respect to these values of the 6 decision variables. Then we have to find out the objective value with respect to the values of these decision variables in the trial vector. So whichever is better, right? Again, how to define the better? It depends upon whether you are solving a maximization problem or you are solving a minimization problem. So whichever solution is better, that solution will go to the next iteration. So whether the trial vector will be better or the target vector will be better. So whichever is providing the best objective value, that will go to the next iteration. In this way, you have to apply these steps for all the chromosomes in the population. Now let us see how to do this now after doing the selection, right? Now we are having the target vector. From the target, we applied the mutation, we got the donor vector. We applied the recombination or the crossover operator, we got the trial vector, right? So before doing the greedy selection, right? Before applying the greedy selection between this target and the trial, you have to do the bounding of the trial vector. So what is the bounding? Because bounding you have to do in almost every optimization algorithm, right? Suppose whatever value, we are having some lower bound, we are having some upper bound of the decision variables, right? If the value of the decision variable, it is and it is exceeding the upper bound, right? In this range it is coming. So this is our actual range is there, lower bound to upper bound. If the value of the decision variable is exceeding the upper bound value, so forcefully you have to make this as upper bound value. I mean, this suppose 10, 20 is there, you are getting some value 30 by applying these operators. So you have to forcefully make this as 20. Similarly, if some value it is going beyond the lower bound, suppose this is -5, you are getting some solution, then forcefully you have to make it as 0. So this is the bounding, kernel bounding, or you can bound the values with respect to your lower bound and the upper bound. That is the LP and the UB. So this step you have to do before doing the selection, right? So mutation followed by the recombination, followed by the followed by the bounding, right? Sorry, followed by the bounding. Then you have to do the selection. So selection, so whatever I told you, you have to evaluate the fitness function or the objective function for all the solutions. Then you have to update the population using the greedy selection. So greedy selection, that means whichever solution is good, that will go to the next population iteration. So greedy selection you are performing after generation of offsprings by all the solutions. I mean, after generating trial vectors of all the target vectors. Right? In that scenario, first you have to do the bounding. After bounding, you have to do the greedy selection. So this is the procedure only. You have to, from the target vector, you have to find out the donor vector. From the donor vector, you have to find out the trial vector. Then you have to do the bounding, upper bounding and the lower bounding. Then you have to do the greedy selection. So this is the procedure for the differential evaluation algorithm. So we have started from one population, right? Suppose population size is 5 + 5. After doing the greedy selection, again you will get another population 5 + 5. So this is the same thing. This is the computation for the differential evaluation algorithm, right? So here you are doing another population, that is a P dash. Same things you have to repeat for this newly generated population. So this step you have to repeat, or this procedure you have to repeat until the termination criteria is reached. So what is the termination criteria? Right, in the you have solved now genetic algorithm, you have solved, and SCA you have solved, SA you have solved, right? So termination criteria, it may be considered as the number of iterations, right? Or there is no improvement in the objective function, objective value. In that case, you can terminate the procedure, right? So now we'll come to the pseudocode where we are providing, right, in the input, we are providing the fitness function or the objective function, lower bound of the decision variable, upper bound of the decision variable. So the lower bound and the upper bound of each decision variable, you can vary also. It depends upon your problem, right, which problem you are solving. NP is the number of population. T is the number of iterations. Scaling factor F, that is used for mutation operator. And PC value, this is used for your recombination operator, right? So till now we have discussed the binomial crossover. So we'll see the exponential crossover also. Sorry, the uniform crossover also we'll see how it works, we'll see. So if you provide this, things you have to initialize, then you will apply the differential evaluation algorithm, you will get the optimized solution. So what we have done, so the step 1, we have initialize a random population, right? Then you have determined the fitness of the population. I mean, whatever the chromosomes are there in the population, we have calculated the fitness value, because fitness value is required for doing the selection. Okay. So what we have to talk to, for T, small t equals to 1 to T. So this is the termination criteria. For capital T number of iterations, you have to repeat the steps. So what you have to done, first we have to do the mutation, then crossover, right? Then for 1 to, right, I equals to 1 to small I, this is I equals to 1 to NP, you have to do the selection. Selection you have to do between the target and the trial, right? Then you have to end this one, then you have to end this main iteration, the termination criteria, right? So what you are doing in the mutation? So this is the same thing, whatever you have considered, your input, output, initialization of the random population, evaluating the fitness value of each chromosome in the population. Now this part is for your mutation and crossover, right? So for I equals to 1 to P, for every chromosome in the population, you are generating the donor vector using the mutation. Then you are performing the crossover to generate the offspring. So offspring means your trial vector. Okay. Then what we have done after doing the crossover, you have done the bounding, right? So for I equals to 1 to NP, you have to bound the trial vector. Then you have to do the greedy selection, right, between this ui, right? Evaluate the f of ui and perform the greedy selection between f of ui and fi. Fi is, that is the initial fitness value from the population, right? So if you do the greedy selection between ui and I, right, then you can update the population. So in the mutation operator only we have seen, right, your that formula we have seen, that is the x dash or xj equals to your xr1 plus f into xr2 minus xr3. This we have done, and here we have done the binomial crossover. This is the recombination operator we have used. This is the mutation operator we have used in the differential evaluation algorithm. Now let us see another type of crossover is there also. You can apply, because you have to know, right, how which operator is working well for your problem and for which type of crossover you are getting good optimum solution, right? So the exponential crossover, how it works, you have to randomly choose an integer n between your 1 to d. So d is the dimension of the given problem, how many decision variables are there. Okay, so randomly you can choose. That's why your randomness is coming here also in the exponential crossover. Then our target is to find out the trial vector, right? So whether the trial vector, it will take the value from the target or it will take the value from the donor. So what we have to do, how to define this one. So once you have defined the value of n between 1 to d, you have to copy the nth variable from the donor vector as the nth variable of trial vector. Whatever n value you are generating, just you have to copy that variable value from the donor to the trial vector. Then again, n minus 1 decision variables values are there. You have to find out those values, right? Whether it will take value from the target or the donor. So for that, what you have to do for the subsequent variables, I mean after the nth variable, you have to generate a random number again between 0 and 1. Here again the randomness is coming. Then depending upon that random number, so this is the random number R. Okay. So if that random number is less than your probability of crossover, so you have to copy the variable from the donor vector to the trial vector. Otherwise, if the R value is greater than PC, you have to copy the remaining variables from the target to the trial vector. Right? Let us do one example so that you can understand how this exponential crossover works in the differential evaluation algorithm. Right? So I have given you different scenarios so that you can understand how to do this exponential crossover. Suppose the dimension, right, d equals to 8. 8 variables are there for our problem. So this is the target vector. The values are given. See, 2, 8, 7, 2, 8, 7, 9, 6, 3, 5, 4. Suppose you have applied the mutation. I got the donor values like this: 1, 2, 4, 8, 7, 0, 9, 2. Now, what is our target? Our target is to find out this trial vector. These are unknown, right? These trial vector values are unknown. So either the trial vector, it will take the value from the target or the donor. So for that, we need the random number here, right? So before generating the random number, we have to generate in the exponential crossover, we have to generate the value of n between 1 and 8. Assume n equals to 3. So what will happen? So whatever, if you see this one, so copy the nth variable from the donor as the nth variable of the trial vector. So this is the third variable, right? So this value, this donor value will be copied here. This is 4. Okay. Next, what you have to do for the subsequent variables, you have to generate a random number between 0 and 1. Right. Now for the next, from this variable onwards, you have to generate the random number. Now let us see how it works. So as the n value is 3, right? So the donor value, this 4 is copied to the trial vector. Initially nothing was there, right? Then for the next number or the next variable, we have generated 0.9. So 0.9 is greater than PC. You see, if R is greater than PC, copy the remaining variables from target to trial vector. So for these remaining variables are means this variable, this variable, this variable, this variable, this variable, this variable, this variable. You see, all the values from the target are copied here. This is the exponential crossover for the remaining variables. So once it will come to the 8th variable, again it will come back to the first variable. All the variables are copied. Now let us see another scenario here. Suppose n equals to 3, PC equals to 8. So 3 means this 4 is copied here first. Okay. Next, for the subsequent variables, you have to generate the random number. So this is 0.5. 0.5 is less than 0.8. So it will copy donor to trial. Again for this is 0.4. Again donor to trial. Again for the next variable, we are generating 0.3. Again donor to trial. Next variable 0.1, less than probability crossover 0.8. So donor to trial. Next variable, you see this is 0.9. So 0.9 is greater than 0.8. So what you have to do for the remaining variables, you have to copy from the target. Now see, from target it is copied. Here also it is copied from the target. Here also it is copied from the target. Right? Now this is the construction of the trial vector applying the exponential crossover. Now see another scenario. If you see, suppose n equals to 6. 6 means 1, 2, 3, 4, 5, 6. This one. This value, donor is copied directly for the sixth variable. Then for the subsequent variable, so for the seventh variable, you have to generate a random number. 0.5 is less than 0.8. So donor will be copied, right? Next variable 0.4. Again, this is less than 0.8. So from the donor, it will be copied. Again, it will come back to the first variable. So this is 0.6. 0.6 is less than 0.8. So again from the donor it will be copied. Next is 0.9. So 0.9 is greater than 0.8. So for the subsequent variables, how many variables are there? From this variable onwards, whatever is pending, for all your target values are copied. Right? So this is your exponential crossover. So you have to apply the exponential crossover or to find out the trial vector, whether it will take from the donor vector or it will take from the target vector. Right? So this is the basic principle of the differential evaluation algorithm. So that mutation strategy, whatever we have done, right, your x dash, xj, we have written xr1 plus f into xr2 minus xr3. So this mutation strategy, you can vary, right? So there are different variations of the differential evaluation algorithm. So the mutation strategy you can represent like this. This is the differential evaluation algorithm followed by x, followed by y, followed by z. So what it represents? So D represents the differential solution or the differential evaluation. X is the vector to be mutated. Which vector you are trying to mutate? Y is the number of difference values. So how many random solutions you are taking the difference value? If you see here, only one difference you are taking among the random solutions, right? So the Y value is 1 here. Okay. And required for mutation. So here two random solutions are required for mutation, right? Because you have to take the difference between these two random. And another random solution you have required to find out the addition. So Z is the type of crossover to be used. Either you can use the exponential or you can use the binomial. So by using the different combinations, you can do the different mutation strategy and you can apply this differential evaluation algorithm to see how the performance of that algorithm changes, right, with respect to a particular problem. And again, it will vary from problem to problem, right? You cannot tell that again D will work for this problem, it will provide the optimum solution for this problem. We cannot tell like that, right? Now let us see what are the different mutation strategy for this differential evaluation algorithm. Right. So first, whatever we have done, right, the first strategy only I told you. This is the first strategy. DE rand 1. So here the Z is not written because Z we are considering either here you can write for either binomial or B or E. You can write binomial or exponential. So this is not written here in the strategy. Z part is not written because only two combinations. Either you can go for the binomial or you can go for the exponential. So what we have seen, what is the expression for the donor vector? Vector spelling mistake. Okay. So this equation we have used for doing the mutation. So V equals to XR1 plus XR2 minus XR3. Right. So how many differences we have considered here? One difference only, XR2 minus XR3. That's why this Y value is coming 1 here. And what is rand here? X is random, is random mutation. So we are doing mutation with random solutions. So XR1, XR2, XR3, these are the random solutions with which we are mutating the original solution. That's why D is rand 1. And what is the minimum number of solutions required in the population or the NP size? This is 4. Because XR1, XR2, XR3, these are the 3 solutions along with the chromosome for which we are mutating, or the solution for which we are mutating. That's why 4 number of solutions are required, minimum number of 4 solutions. Now there are other mutation strategy, that is the DE best one, right? Instead of the 1 means your random difference, random solution difference is 1. Here you see the equation will change only. F of XR1 minus XR2 best means the best solution will come for the mutation. That is the X best plus F into XR1 minus XR2. So here the difference is 1. This difference, this is counting for the Y value. So what is the population size, minimum population size? Now 1, 2, these are the 2 random solutions and the chromosome for which we are mutating, because best will come out of the chromosome for which we are mutating and XR1 and XR2. So the minimum population size will be 3. Now the third strategy is DE rand 2. So here difference is 2. So you see the equation is changing here. F into XR2 minus XR3, F into XR4 minus XR3. That's why this is the first difference, this is the second difference. That's why the Y value is 2. Again, rand means 1, this is also random. So the chromosome for which we are mutating, right? That mutation, that chromosome is not taking part in the mutation here. That's why rand. Okay. So how many solutions are required, or what is the minimum population size here? 1, 2, 3, 4, 5. And the chromosome for which we are finding them or doing the mutation. So 6. Okay. So DE best 2. So instead of, right, 2 means again same. This is the first difference. This is the second difference. And best will involve in the mutation. So what is the minimum population size here? 1, 2, 3, 4. And this is the 5. The chromosome for which we are mutating. So the minimum population size equals to 5. Then there is another strategy here, DE target to best 1. So here one random solution difference is there. If you see the equation, F into XR1 minus XR2, this is the random solution difference, it is only counting. Target to best means, right, what is the difference between the target and the best also, it is involved in the mutation. If you see F into X best minus Xi. So the Xi in all these 4 cases, the target for which we want to do the mutation, that is not involved in the mutation expression. But here, the last mutation strategy, target to best, this X best minus Xi, this is involved. So Xi for which we are mutating, right, the target vector, that is involved in the mutation operator. So for this, how many, what is the minimum population size here? This is 1, 2, and out of this, that is 3. So total minimum population size, it should be 3. Right. So in this way, you can do different mutation strategy, right, to solve the optimization problem by using the differential evolution algorithm. Right? Now let us solve a small problem. Right. So suppose we have to minimize the sphere function. This is the, we have to minimize summation of I equals to 1 to n xi square. Suppose the lower bound of all the decision variables are 0, upper bound is 10. Okay. So the dimension D equals to 4 here, we have seen. We have considered. Suppose we will consider n value equals to 4. Because we will do the hand calculation, right? So for the hand calculation, we will consider the number of decision variables, suppose 4. I mean, suppose x1 value is 2, x2 is 3, x3 is 4, x4 is 5. So if these are the 5 values of the decision variables, so your f of x, or the objective function, this equals to, this value will be x1 square plus x2 square plus x3 square plus x4 square. So whatever you will get, right, whatever you will get, that will be the objective value. So for this problem, what is the solution? All values should be 0, then only it will minimize, right? You have to minimize this function so that, right, the values of the x1, x2, x3, x4 you will get, so that the objective value, that is the f of x, it should be minimized. This is the sphere function we have to use. Now let us fix the parameters. What we have to initialize the parameters. Assume the population size equals to 5. Number of generation t equals to 10. Right? Crossover probability suppose 0.8. And this is the suppose scaling factor is 0.85. So these are the parameters we have to use in the differential evolution algorithm. Right? Now what we have to do? We have to generate the random solutions within the domain of the decision variable. So how many decision variables we are considering? 4, right? So 4 values if you see, x1, x2, x3, x4. If you see randomly, so the population size equals to 5 we have considered, right? So 5 different solutions we are generating. This is the chromosome 1, chromosome 2, chromosome 3, chromosome 4, chromosome 5. So if you see all the values of these chromosomes for x1, x2, x3, x4, all the values are coming in the range 0 to 10. So you have to initialize in that way. Initial values. Randomly you have to initialize in the range 0 to 10. Next, what you have to do, after initializing the population, you have to find out the objective value of that chromosome, of that solution, right? So how will you get x81 now? You have to find out 4 square plus 0 square plus 1 square plus 8 square. How much it is coming? 16 plus 1 plus 64. So 65 plus 16, 11, 7, 8, 81. Right? Like that, you can calculate the objective value or the fitness value, because by using this value, you can determine whether the solution is better. Because you have to apply the greedy selection between the target vector and the trial vector. Right? So initial population, you have fixed the parameters like this. Right? So I will show you for one iteration only. I will not show you for 10 iterations. So this is the this is the initial population we have generated. Population size equals to 5. Then we have calculated the objective value. Next, what we have to do? Next, what we have to do? We have to apply the mutation operator to the target vector to find out the donor vector. Right? Now, this is the target vector. So how many target vectors are there here? 5. 1. This is the second. This is the third. This is the fourth. This is the 5. So this solution, we are trying to explore a good solution from this solution. So the solution is 4018 because the values of x1, x2, x3, x4 are 4018. We have to apply the mutation operator to get a donor solution. Similarly, same thing we have to apply for this 3021. So I will show you the detailed calculation for this 4018. Similarly, you can do for the remaining chromosomes. Right? Now what we have to do? You have to apply the mutation to find out the donor vector for the trial vector. So we have seen here the solution is 4018. So we are doing the mutation for the first chromosome 4018, right? So for that, what is our equation if you remember? Xj, right? Sorry. Vj, this will be donor vector. 1 minute. Okay. So Vj will be xr1 plus f of xr2 minus xr3. So we are doing the first mutation strategy, the DE rand 1, because this is really easy calculation. That's why I am solving this way. So we can similarly can do for the other mutation strategy. So for this, what we have to know, f is scaling factor already we have initialized to 0.85, right? So the value we have to take in the range 0 to 2. So what is XR1? What is XR2? What is XR3? You have to find out. So for that, you have to generate this R1 value, right? What is R1? What is R2? What is R3? That means which solution? So there are 4 solutions are there. Sorry, there are 5 solutions are there because my population size NP equals to 5, right? Here 5 solutions are there. So what we have to do? We have to select 3 random solutions out of these 5 to determine which solutions will take part in the mutation operator, right? So what we have to do now, what is the constraints if you remember? So for this we have to find out the mutation. So we have to generate R1, R2, R3 such that R1 not equals to R2, not equals to R3, not equals to this xn. That means for the remaining 4, you have to select 3 distinct solutions, right? So this is 1. So from the 2, 3, 4, 5 solutions, you have to select R1, R2 and R3. So you see randomly this is only. So R1 is 4, R2 is 2, R3 is 3. Let us assume we have generated 3 values from the remaining. So now you see, so for the first chromosome, we have to find out the donor vector. Now this R1 is 4, R2 is 2, 3. So 4 not equals to 2, not equals to 3, not equals to this chromosome for which you are mutating. Now your condition is satisfying, right? So next what we have to do now, let us see what is the donor vector with respect to this 4018. Now you apply the formula XR1. So XR1 means R1 is 4. So X4 plus the scaling factor F into XR2 is X2 because R2 value we are taking 2 minus XR3. R3 is 3. So this is X3. So what is X2? What is X3? What is X4? These are the values only because this is X1, this is X2, this is X3, this is X4, this is X5. Now you put the values in that equation. So x4 is 2149. This is the 2149 is the x4. Right? So this is the 2149. Then 0.85 is the scaling factor. X2 is, if you see the X2, 3197. This is the X2. So this is 3197 minus X3. X3, what is the value? 0315. So this is 0315. If you solve this equation, right, you will get this value. So this is the donor vector, right? We have started for this. We have started from this solution, right? We have started for this chromosome in the target vector to mutate, right? After mutating, what we are getting? After mutating this 4018, we are getting this one, 4.55 minus 0.7, 10.8, 10.7, right? So this is the donor vector to respect to 4018, right? Now what we have to do? So before doing the trial vector, right? So what you have to do? We have to construct the trial vector, whether the trial vector will take value from this one or from this one, because this is the x, this is the d, right? So for that, what you have to do? You have to generate d random numbers to generate the trial vector. So here the example is solved by using binomial crossover. So you can solve by using the exponential also, binomial crossover. Okay. So for binomial crossover, if you remember, so for the trial vector u, we have to generate random numbers. How many random numbers? Because my decision variables are 4, right? So I have to generate 4 random numbers. Assume 0.3, 0.2, 0.9, 0.21, 0.6. Now we'll see whether the trial vector, right? Whether it will take the value from x or whether it will take the value from d. Now let us see what is that. So how to determine the trial vector? So this is the target vector for which we have to find out the trial vector, right? So we found the donor vector by using this mutation operator, right? Then we have generated 4 random numbers with respect to 4 decision variables to find out whether the trial vector will take value from the donor or it will take value from the vector target, right? Because PC value, you see, phi value is 1, PC value I think 0.8 we have initialized. Phi is 1, PC is 0.8. So 0.3 is less than 0.8. So it will take the value from the donor vector. 0.9 is greater than 0.8 and I, this is the j, right? This is the 2 not equals to 1. That's why it will take the value from target vector. This is 0.2 is less than PC, 0.8. So donor vector. 0.6 is less than 0.8. So this will also take the value from the donor vector. So what is the trial vector? Now we have started from 4018. We have started from 4018. Donor vector we got 4.45, 0 minus 0.7, 10.8, 10.7. So what is the trial vector now? This is the target, this is the donor. So the trial is, now this is the donor vector, that means 4.55. This is the target 0. This is the donor 10.8. This is the donor 10.7. Now we are able to change this solution 4018 to this solution 4.55, 0, 10.8, 10.7. New solution, right? So for that you can check for bounds, right? Now we are getting the trial vector like this. So this value, because our lower bound and the upper bound is 0 to 10, right? So after bounding, you are getting 4.55, 0, 10, 10, right? So this is the, so we have started from 4018. For 4018, we have done the mutation. Then we have applied the binomial crossover. And finally, what we are getting? 4.55, 0, 10, 10. So whether this solution is better than this solution or not, we have to, for that we have to do the greedy selection, right? So how to do the greedy selection? For this, we have calculated the objective value as 81, right? So if you do this one, you will get some objective value because our target is to minimize, right? So which one is best? We have to find out that one. Now you see. So for this, I have shown you the calculation for this first step only. For the remaining steps, I am not going to show the calculation. You can do by your own, right? So the target is 4018. We have chosen 3 random numbers R1, R2, R3, 4, 2, 3. We have constructed the donor vector like this. We have generated 4 random numbers with respect to 4 decision variables. Then the phi value we have considered like this, or you can consider the phi value same for all the target also, right? Then we have got the trial bounded as this one, 4.55, 0, 10, 10, right? For the remaining, right, for the x2, x3, x4, x5, you follow the same procedure, but with different random solutions, because it will change as per our constraints, right? So you will get this. So you can verify. This is the sample solution is there. If any calculation mistake is there, you can find out. Right? But I hope there is no calculation mistake here. Okay, so now let us see what we have to do. So now we got this trial bounded. So whether we have to choose this solution or this solution, because this is our initial population. So what will be our next population? So whether we have to consider this population, or we have to consider some population from target, some population from trial, right? So for that we have to do the greedy. So for greedy selection, we have to evaluate the fitness of our trial vector. So this is the trial vector 4.55, 0, 10, 10 up to this one. So now we apply that f of x, right? F of x is summation of I equals to 1 to 4 xi square. If you apply, you will get these are the fitness values, right? So the comparison is here in the next slide, right? So these are the trial bounded. In this slide, it is there. Let's see. So this is the target vector. We have initially the population is like this, right? So the old fitness value is like this, okay? And the trial bounded, after doing the mutation and the recombination, we got these are the trial bounded values. The fitness value of this trial bounded solutions are this. Now what will be our, this is our original population P1. So what is the population for the next iteration, right? Now you see, you have to compare between this and this. So what is there here? If you see, its fitness value is 81, its fitness value is 222.70. So as this is a minimization problem, so this solution will give, this will go for the next population. That's why this is represented as the red color. So 4018 will be selected. Now come to the next one. This fitness value is 140, here 140. So this is better, right? As this is a minimization problem. So for the second chromosome, this solution will go to the next iteration, right? So here we are considering 4018. First we have considered 4018. Next 4.4008, 5.55. Okay. Third one, if you see, this is the 35, this is 171. So this is better. So third one, this is selected for the next 0, 3, 1, 5. For the fourth one, this is better, right? So this has to be selected. So 0, 3.7, 1.2, 1.3. Next, for the last one, this is better. So 1, 2, 8, 1, 2, 8, 3 will be selected. So we have started with this population size 5. We have applied the mutation, we have applied the recombination, we have done the greedy selection, and we are getting another population, right? So previously what was there, if you remembered in the previous, right, what was the minimum value, fitness value out of this 5, right? 81, 140, 35, 102, 78. So which one is minimum? This is the minimum initially, whatever random we have generated. Now, after applying one iteration of the what you call that is the differential evaluation algorithm, what we are getting? 81, 114.16, 35, 16.82, 78, right? So what is the minimum we are getting here? 16, right? Here you are getting 35, here you are getting 16. So after doing one iteration, we are able to minimize the function from 35 to 16.82. So if you repeat, right, same things, your process you have to repeat by taking this population now. If you repeat a large number of iteration, it may converge towards the global optimum solution. So you know the global optimum solution for this problem is 0, right? F of x should be 0, and for the all values x1, x2, x3, x4, it should be 0, right? So this is the explanation for this PR function, how to minimize a function by using the differential evaluation algorithm, right? So this is the population for the next generation, whatever we have selected, and by using, right, by using this population, you have to repeat for the t number of iterations, right? So this is the basic explanation of the differential evaluation algorithm. If you are having any doubt with respect to this one, you please ask, and I will show you the coding part for the differential evaluation algorithm. Then we'll go for the some improved D algorithm also. Any doubt up to this? Let me open the MATLAB code. Just give me 2 minutes. Is this visible? The MATLAB code? Please, any one of you can confirm. Is this visible?
Yes, madam.
Okay. Okay, so the same sphere function we are going to minimize here. So this is the simplest sphere function, the problem you have to minimize. You can write here because I'm not going to write the code here. So this is sphere function you have to take, right? Summation of xi square. Right? So this is the simple sphere function. So what you have to do for the differential evaluation algorithm, all right, you have to fix the lower bound of the upper bound of the all the decision variables. So for simplicity, I kept the lower bound on the lower bound as 0, upper bound is 10 for all the decision variables. So you can change here, right? Or you can write your own programming. You can do your coding, right, by your own convenience. Then we have to solve this sphere function, right? So the problem we have to optimize here, that is the sphere function we are trying to optimize. So the problem is, so I'm calling that sphere function here, right? Next, what are the parameters we have seen in the differential evaluation algorithm? Your population size 5, I have considered 5. So number of iteration is 15. Your crossover probability value, PC value is 0.8. And the scaling factor, right, this is the 0.85. These are the initial values, parameters you have to initialize. Okay. Then what you have to do, you want the fitness value, right? Fitness value of the trial vector, fitness value of the target vector, right? And the dimension of the problem, how many decision variables for your problem, and trial solution where you have to store the trial solution. Okay, so these are the some metrics I have initialized. So the F is the matrix to store the fitness value of the target. Okay, FU is the fitness value of the trial solution. Okay, so D, that is the length or how many decision variables I want, right? Or you can write n equals to 4 like that, right? So as I have initialized, right, lower bound I have fixed for the 4, right? If you take the length of LV, it will return 4 only. So there are 5 only, sorry, 5 I have taken. So the decision variables will be 5. Number of decision variable will be 5. D will be 5. Then this is the U matrix that will store the trial solution. So that solution will go for the next population. Okay. So what we have to do, first we have to generate the initial solution. So randomly we have to generate the initial solution in the range lower bound and upper bound. So what is the population size? Population size is NP, right? So as per the population size and with respect to your lower bound and the upper bound, the population, initial population will be generated randomly, right? In the range 0 to 1. Here we have fixed. Next, what we have to do, we have to find out the fitness value, right, of individual solution or individual chromosome. So for P equals to 1 to NP, so we have to call that function because sphere function I have, right, here I have called the sphere function, right, PROB, this sphere function I have called here. So what you have to do, you have to pass individual chromosome to this function and it will return the fitness value of individual chromosome and that will be stored in the array F. Right? So that the size of the array will be number of population size. So these are the initial part, right? Next, what you have to do, you have to do the mutation for each chromosome, right? The target vector, then you have to do the recombination crossover, then you have to do the bounding, you have to do the grid selection. This thing you have to do for a number of iterations. So that is the outer loop for t equals to small t equals to 1 to capital T. For t number of iterations, you have to do, right? So for NP number of population, right? Population size equals to NP. So every solution in the population, right? NP size, you have to apply the mutation. So for the mutation, what you have to do, if you remember, you have to generate 3 random solutions, and those 3 random solutions should be different for the solution for which we want to do the mutation. So this is the candidates equals to 1 to I minus 1. So I you have to exclude from that NP, and from the remaining you have to randomly choose 3. So for doing that part, these are the 2 statements you have to write. You have to select 3 random partners which are not equal to each other and which are not equals to I also, right? So what will happen after getting this R1, R2, R3, 3 random numbers, 3 random solutions from the population? What you have to do? This is that index. It is returning the index IDX. So x1, x2, x3, you find out which one is the index. Then this is the simple DE, the random variation with the number of difference 1 we have considered, right? The difference mutation strategy, DE rand 1 we have considered here. If you want to do the other mutation strategy, you have to change the equation here only, right? It depends upon how many random numbers want, right? That's condition you have to write here. So this is for your DE with random mutation with 1 difference, right? So this is you are generating the donor vector with respect to the first solution now. Then you do the crossover. So this is the written for your binomial crossover. You have to generate the phi value. So phi value you have to select randomly from, right, out of the 1 to D dimensional problem. Then you have to write that OR and the AND equation, right? If R is less than equals to PC or phi equals to J, right? Else that part, right? So accept the donor part, accept from the donor, otherwise accept from the target, right? So this part is for crossover, okay? Then what you have to do after doing the crossover, you have to do the bounding. Then you have to do the grid selection, right? So bounding, how you have to do? You have to check whether if it is exceeding the lower bound or it is exceeding the upper bound. That you have to check, right? If it is exceeding, then what you have to do is minimum it is taken, right? So if it is exceeding the upper bound value, you have to forcefully make it to the upper bound. Similarly, in the case of lower bound, right? So this is for bounding between for the trial solution, so the trial vector. Then after doing the bounding, you have to do the grid selection. So for doing the grid selection between the target and the trial, you have to find out the fitness value of the trial. So what you have to do, you have to pass this trial vector again to this, the sphere function, right? So the sphere function will return the fitness value of this trial vectors. Now what you have to do, you have to do the grid selection between the trial and the target, right? So you compare. So as this is a minimization problem, whichever is minimum, that population or that chromosome will enter into the new population. So this part is written for that, right? Next, what you have to do, you have to find out the best fitness value. Whichever you are getting the right minimum solution, that will be the solution of the run problem. Okay. So this is the sphere problem. 1 minute. So if you run this problem, how many iterations are there? I think very small. 15 iterations, right? Okay. If you run for the 15 iteration, what you are getting? See. You are getting for x2, x3 and x5 we are getting 0. But till now x1 and x2 we are not getting 0, right? So for this, you have to iterate for a more number of times. So that gradually it will converge towards the global optimum solution. Because solution we know already, right? 0, 0, 0, 0, 0. If you change the number of iterations here, let us change it. Suppose, let us see, 100. The changing, you see, at the end you are getting 0, 0, 0, 0. Right? So this is all about your basic DE algorithm. Right? You can change the objective function here. What is the objective function? And what are your decision variables? How many decision variables? What is the upper bound and the lower bound of your decision variables? Right? Depending upon that, you can write the D random 1. And if you want to write the different decision strategy, you have to change here. Right? You have to change the mutation function, this one. This is different. This part you have to change because mutation strategy, if you will change, this part will completely change. Because depending upon the mutation strategy, the number of random solutions generation will be different, right? And you can try for this exponential crossover also. This is for binomial crossover, so you can try for exponential crossover also. Okay. So this is the basic differential evaluation I told you. So there are some improved version of the differential evaluation algorithm. So what is the problem in the differential evaluation algorithm? Generally, how to avoid the local optimum solution and how to improve the convergence performance of the differential evaluation algorithm. Right? So how to deal with this? So for solving, right, to find out the solutions for these two types of problems, there are some improved D algorithms are there, right? So one of the improved D algorithm is there. There is some enhanced mutation strategy you can use, or you can use some adaptive strategy to control the parameters, right? So what are the parameters we have seen? We have seen the scaling parameter, probability crossover, right? Those are the control parameters. So how to change those parameters and what are the how these parameters affects the optimum solution of the differential evaluation algorithm. So as per that, some new equations you have to introduce into the mutation as well as into the crossover, right? So in the improved D, right? So the enhanced mutation strategy, this is generally based on the D rand one. So you can change the mutation strategy here. So generally what happens here, which takes into account the influence of reference individual on mutation, right? So reference individual means we are writing that whenever we are doing the mutation xj, right? Sorry, Vj we have written xr1 plus f into xr2 minus f xr3, right? So this is the referential individual. So this has some impact on the mutation, right? So the proper value, you have to set the proper value for this one also. So how it happens in the enhanced mutation, we'll see. So for changing this value, right? So how the XR1 affects on the performance of the D and how to change the value of X1 in every iteration, depending upon that, that is the enhanced mutation strategies introduced into the D. Similarly, for finding the proper values of scaling factor F and the crossover probability PC, there is some novel adaptive strategy also there. So for every generation, this value will change and this value will change, right? So what are the effects, right? How they are affecting the performance of the differential evaluation algorithm, we'll see. Now this is the basic mutation equation we have used, right? This is the donor vector for the iteration G plus 1. G is the number of generation here. So the previous generation XR1 plus scaling factor into previous generation XR2 minus previous generation XR3. This is the simple equation we have used. Now let us see the reference individual is this one. This one we can call the reference individual. So this has an important role in regulating the balance in the evolutionary process. That means towards the optimum solution or the global solution. So what happens in the early stage of evaluation? Early stage means during the initial iterations of the differential evaluation algorithm. What happens? Most individuals are far away from the optimum solution because we are generating the random solution. So we are assuming that most of the solutions are far away from the optimum solution. So if you put a larger value, right, xg, this reference value is larger value, it will help to jump out of the local optimum, right? But what happens in the latter stage of evolution? What will happen? As we are applying the mutation crossover, then we are doing the greedy selection. Most individual gradually approach towards the global optimum solution, right? So if you put a larger value of xgr1, this reference solution, towards the latter stage of the evaluation, right? So what will happen? It will deviate from the current direction of the evaluation, right? So that is not in the favor of the global convergence. So what we have to do? So during the initial generation of the differential algorithm, this value should be higher. And as the generation progresses, right, or during the latter iteration stages, we have to minimize the value. That is the concept here, right? Depending upon that, we can design some enhanced mutation strategy in D algorithm, right? So that improved mutation strategy is that this value we are changing in every iteration. You see. So here we have introduced another variable alpha, right? So alpha, this has to be multiplied with the reference individual. Remaining is same here. This part is same. So this alpha value will change in every iteration. So how to change the alpha value? That is the 1 minus r. This is a random number you have to generate. So here again the randomness is there, right? R to the power 1 minus g by g max. Suppose my number of iteration I am iterating for 100, right? So for the current iteration 2, for the second iteration, What is the value of alpha now? 1 minus, you generate some random number, suppose 0.7, right? So 1 minus current iteration is 2 divided by maximum iteration is 100 square, right? So the alpha value will change in every iteration. If the alpha value will change in every iteration, XR1G, this reference value will also change in every iteration, right? So that problem, the deviation from the global optimum, right? That problem will be avoided up to some extent if you use this improved mutation strategy. Right? So here this alpha belongs to the 0, 1. You will always get a value in the range 0 to 1. So, right, so these are the same thing, that is the FICR, these are the reference factor is your, this XJI, scaling factor is F, CR is the crossover probability, right? So your G denotes the current generation number, R is a random number in the interval 0 to 1, whatever I explained here, and G max represents the maximum generation number. So this is the one improved enhanced mutation strategy on the differential evolution algorithm, right? So whatever we have discussed in the previous slides, right? It is observed that the value of alpha G, it is very high during the early evolutionary stage. So if it is very high, this, if you took this value, this is also very high. So there is a chance that more solutions they will that they can skip from the local optimum problem, right? And during the latter stages, as the evolutionary generation increases, this value decreases because the equation is set like that. Right? If it decreases, so what will happen? This value also decreases. So the deviation from the global convergence problem, that will be eliminated here because we are shrinking the source space scope. Here we are expanding the exploring the source space. Here we are shrinking the source space. So that is the advantage of the enhanced mutation strategy, right? So you can add this enhanced mutation strategy in that basic D program also, right? So what you have to do there for that one minute. So what you have to do in that outer loop, right? Inside this D algorithm, before this iteration is changing, right? This for loop of for t equals to 1 to t, because this we are writing for generation, right? So before ending of that, here I have written. So here you can write that part for the how to change that reference variable. That alpha equation you write here, and that alpha you have to introduce the, here you have to change the, what is that, your mutation operator you have to change here. Mutation operator is here. You have to change the mutation operator here. You have to introduce the alpha here, right? And you have to update the alpha value before the end of this number of iterations. Here you have to update the alpha value, right? Similarly, for updating F and PC value also, some other methods are there. I will tell that one also, right? Then your adaptive strategy can use to control the parameters. So there are two parameters here. We have seen that F is the scaling factor, PC, that is the crossover probability, right? So let us see what is the effect of this capital F and the PC on the solution space. Whenever you have the number of generation or the number of iteration is increasing, how the D algorithm will behave, right? So during the mutation operator, the scaling factor, what it doing? It affects the reference individual through the difference vector XR2 minus XR3. So this is called generally the perturbation, right? So if the value of F is very high, you will get a very larger perturbation value. So this will helpful to maintain the population diversity, right? But it will reduce the search efficiency of the algorithm because it has to search for all the diversity of the population. If you decrease the value of small, right, F, the smaller value of F, what it will do? It will improve the conversion speed, but the loss of population diversity, right? So there may be chance that it will fall into the local optimum and it will get the premature conversion. So in order to avoid that one, you have to, right, you have to find or properly tune the value of F. That means during initial iteration, some value F is there, and during the lateral generation or every iteration, you have to change this F value. Right? Similarly, this probability crossover PC value or CR, probability crossover. So what is the meaning here? It determines the contribution of the mutation vector to the trial vector. Because when we have done the binomial crossover, right, or the exponential crossover, depending upon the relation between R and PC, right, we are selecting whether the trial vector will take value from the donor or it will take the value from the target. So the CR or the PC determines the contribution of the mutation vector to the trial vector. So if the value PC is very high or the CR is very high, it facilitates the expansion of the source space, thus accelerating the convergence, right? So if the value is very small, it is not to the benefit of exploring the search area. So you have to adaptively adjust the value of F and PC or CR. Here in this slide, it is written CR, right? CR and PC are same. So adaptively, F and PC should be adjusted in the differential evolution algorithm to get better solution. So how to do that one? So this scaling factor Fi, it will change in every generation. G is the generation or the iteration. How it will be changed? So this is the small f, it is the fitness value. Fitness value, right? So F max G, for that iteration, what is the maximum fitness value, right? Minus Fij, for that generation, what is the fitness value, right? Then F of G mean, what is the mean value of the fitness value? Similarly, your PC value, PC, this is the crossover, probability crossover. You can change in every generation by using the fitness value in that current generation minus the minimum value in the fitness value divided by the mean. So if you do this one, in every iteration, your F and CR will change so that you may get better solution by using the differential evaluation algorithm. So that part you can add here in the same thing, whatever I told here. Here in this part, just before the end of the generation or the number of iteration, you can update the alpha value, you can update the F value, you can update the PC value. And you have to change the mutation as per that one because the operation it will change here. So here the basic, this is the basic D with random mutation with one difference operation. So you can try for different mutation strategy, whatever I told for the D algorithm, along with the enhanced mutation strategy and the adaptive control parameter, the adaptive strategy to control the parameters of the genetic algorithm. Right? Okay, this already I explained. So this differential evolution, right? There is the binary version of the differential algorithm also there. Differential evolution algorithm is there. So depending upon your problem, suppose you want to select, you have to do some selection of the features from a given data set, right? That also you can do by using this binary D, right? Binary D, right? Generally your feature selection and the instance selection. Suppose you are having a data set and you are having, suppose 10,000 data points are there, right? So which 10 points or which instances are required, right? They are relevant, related to the problem, right? Those instances also you can select by using this binary D. That means, so the binary D, the constraint you have to follow that every solution, right? The target, donor, or the trial, they can take either 1 or 0 value. Right? So you can apply this, whatever D we have considered, you can apply, only you have to convert that value either into 1 or 0. So for that, you can use the sigmoid function, right? The output, whatever output you are getting in the DE, you can apply the sigmoid function. So you will get that value in the range 0 to 1. If you apply this one, 1 by 1 plus e raised to the power minus output, whatever you are getting, right? So you generate a random number. If that random number is less than this sigmoid value, you have to assign that variable as 1. Otherwise, you have to assign that variable as 0. So you can go for the binary differential evaluation algorithm by using this exponential, sigmoid function. Okay. Okay. Then there are some classification. If you have solving some problem by using the machine learning algorithms, right? We are having some classification problem, right? So if you want to, suppose we are having some data set, right? And suppose there are two classes. Suppose your n number of attributes are there for the data set, right? And the last column it represents, suppose the class to which the instance belongs. Suppose 0, 1, 0, 1, like that. The data set is like that. 1 to 20 attributes are there, assume. So 21th column, it represents whether the data belongs to the class 0 or class 1 or positive or negative, right? So how to find out, right, the fitness function for this classification problem? So this is a classification problem. So which features are relevant, right? Out of 20 features, which features are relevant for doing the classification, right? So that type of problem also you can solve by using the binary D. But here fitness function, right, you can use the fitness function in different manner. So fitness function you can consider as the, right, your performance of the machine learning model also you can consider, like your All right, different performance measures are there for the machine learning models for the classification problem, right? Like we are having accuracy is there, right? If your data set is balanced, you can go for accuracy. Your precision is there, right? You are having recall, if you are having F measure, you are having Z mean, you are having AUC, you are having MCC. So many parameters are there, right? You can go for. So the fitness function, you can use either one of these, right? One of these parameters as the fitness function, and you can apply your D algorithm, right, to find out which features are relevant for your classification. Or for the classification problem, without using this accuracy, precision, recall, the machine learning performance measures, you can go for this inter-class distance and the intra-class spread also, right? So how to find out this inter-class distance and how to find out the intra-class spread, and how to find, how to write the fitness function for the classification problem, right? If you are using any binary version of the optimization problem, right? So what is the inter-class distance? So whenever we are having the classification problem, so inter-class distance, that is a measure of separability of the classes, right? How much separated the classes are, that is the inter-class distance. So this should be very high, right? The separation between the classes, it should be very high. So our objective is to maximize this one. So in a data set, the larger the distance, the further apart and separated the classes are. So we have to maximize this one. Therefore, a big distance means that the classes are more distinguished and there is less overlap between the classes. So how to find out this inter-class distance, right? So for finding the inter-class distance, you can follow, this is a simple algorithm, right? So it will work for multi-class problem also, right? Not for binary, it will work for multiple classes also. So to find out the inter-class distance, right? So what you have to do for all the classes, right? So first you find out what are the instances belonging to this class. Then you have to find out the mean instances from these instances with respect to this class. Then you find out some representative of that instances for that particular class. Then what we have, for each class you have to do this one. Suppose we are having 2 classes, for each class we have to find out this one. Next, what you have to do, as our objective is to find out the inter-class distance, so you initialize the distance equals to 0, right? Then for all the instances, right, belonging to, for all the instances, what we have to do, we have to find out the class distance now, right? So class distance equals to 0 now. Suppose the number of links in the distance equals to 0. So for all other instances, right, representative, res means representative instances, right? What you have to do, we have to find one instance I1 and in the res and one instance RE2 that are not in the res, right? So what is the distance between these 2 instances we have to find out. So here you can use the Euclidean distance or cosine similarity, right? You can use this distance to find out. Then you find out the links, number of links equals to, it will be added by 1, right? Then you and this one, this will be entered, right, for all the instances. Then for all other instances, then this is for all the classes, right? So how to find out the distance? You have to find out the distance equals to, for all the classes you have to sum this distance. Then what is the inter-class distance? Inter-class distance will be whatever distance you are getting divided by total number of classes. So this inter-class distance, your target is to minimize this one, right? So, sorry, you have to maximize this inter-class distance. So this can be considered as the fitness function in the classification problem. Or you can merge this inter-class distance and the intra-class distance also into a single fitness function. So what is this intra-class spread? Intra-class spread, this is the measure of how spread out a particular class is, right? That means within a class, right, that distance should be minimum. That is the meaning here, right? Therefore, a smaller spread is preferred for this intra-class spread. So the spread of a class is given by the spread of its features with respect to individual classes in the problem. So how to do this one, how to find out? This is for using only the variance of the features with respect to classes we can do, right? So intra-class spread, we have to minimize here. So you first you calculate the spread of each feature with respect to each class, right? So here for all the features, you initialize the feature spread equals to 0. Then for all the classes, the feature spread you find out, right? That is the sigma, that is the variance of the feature with respect to the class, right? So with respect to all the classes, you find out this one. Then how to find out the overall spread? You initialize the intra-class spread equals to 0. Then for all the feature spread, you find out the intra-class spread equals to summation of all the feature spreads. Right? So if you find out this one, then you can write, you can use separately. Either you can maximize the interclass distance. This is one objective function you can consider, or you can minimize the intra-class spread, or both, right? Multi-objective you can use. You can maximize the interclass and you can minimize the intra-class. So for combining this one, what you have to do? So this is the spread generally you have to calculate, right? Whatever in the previous algorithm I have shown you, how to calculate the spread with respect to feature with respect to a class. Okay. Then this is the multi-objective function. You can maximize the interclass distance and minimize the intra-class spread. So for that, you can write different way. You can formulate the multi-objective function. The spread plus alpha into, this is the cardinality of the features. How many features you are using divided by your interclass distance. Right? So the alpha, right? So the alpha into f, cardinality of, this is added to the spread and the numerator to control the weight ratio between the spread and the distance. So if the smaller constant you are using, so more weight we are giving to the spread, right? So therefore, you have to adjust the weights of the spread and distance, and the number of features automatically it will be adjusted. So like that, you can use the fitness function for the, right, for solving any binary classification problem or multiple classification problem, to solve that, to solve the feature selection problem, or you can do for the instance selection by using this difference evaluation algorithm. And you can use the difference mutation strategy with respect to the different, right, mutation strategy you can use. You can use the enhanced strategy, enhanced mutation, or you can use the adaptive strategy to control the parameters, right? And you can do, if you're having a binary problem, right, selection, feature selection, instance selection, you can go for this binary differential evaluation algorithm, right? So till now we have, right, we have till now PSO has not been discussed till now, right? So GA is there, right? GA we have discussed, and we have seen the basic difference between the GD and the GA. So GA we have, right, we only have started from the selection, then crossover, then the mutation, right? But in the D, what we are doing here, we are doing the mutation, right? Mutation is different here. Mutation, recombination of the crossover, then we are doing the greedy selection. Okay, and that is the basic difference between your differential evaluation and the genetic algorithm. And coming to the TLBO, Sarah has explained today, right? There are two phases, your teacher phases and the learner phases, right? So how the teacher is interacting with the students, then the second phase, how the students are interacting among themselves, right? Depending upon that, you are changing the population from one iteration to another iteration, right? So the PSO, it has not been discussed. I think day after tomorrow, madam is going to discuss about the particle swarm optimization algorithm. So here there is no phases like TLBO. Simply we have to update position and the velocity value. And the differential evaluation also we have seen there are no phases like your TLBO, right? Here only we are doing the like mutation of crossover selection like GA, but the sequence is different. Your convergence in the TLBO is monotonic. Either it will increase or decrease. Right? Here also PS also monotonic. D also it is monotonic. And what are the parameters we are using in the TLBO? We are using population size termination criteria. Right? If you see, right, with respect to this D, there is population size is there, termination criteria is there, F value is there, PC value is there. Right? So if you compare with this one, your TLBO, this has no algorithm specific parameters. Only population size and the termination criteria are sufficient, right? That's why this algorithm TLBO will work for many problems, right? And the PSO, we are having number of parameters. They're like your population size, termination criteria. With respect to this one, we are having inertia constant W is there. C1, C2 acceleration constants are there, right? If you have to properly tune these parameters. Otherwise, your solution it will vary, right? And the generation of solution, what you are doing in the TLBO, always you are finding the mean and the best solution, right? By using that, you are going to the next iteration. And in the PSO, using the velocity, you are updating the velocity and the position. You are finding the P-based, G-based, and then by using this one, you are updating the solution and you are choosing the solution from the next iteration. But the differential evaluation, what we are doing, we are always we are doing the greedy selection. So greedy selection between our first individual randomly whatever we are generated or the target, and after doing the mutation and the crossover, we are getting the what we call that is the try. So always the best solution we are selecting to the next population. Right? So these are the comparisons between the different algorithms, right? Whatever many more algorithms are there. So you can compare now each and one algorithm, how the algorithm works and how they are different from each other. Right? I think this is all about your differential evaluation algorithm. So these are some of the references, some of the applications are there. You can go for, or you can search for your problem domain, right? What are the problems have been solved by differential evaluation algorithm, and which mutation strategy or whether improved differential evaluation or the adaptive differential evaluation has been used or not. You can verify so that you can find out some better solution for your given problem. So this is all from my side. If you are having any doubt, any question, you please ask.